The largest structures in the universe may have begun as quantum fluctuations smaller than anything visible stretched across cosmic distances during a fraction of the universe's earliest history. Cosmic inflation is the idea that space itself once expanded at an extraordinary accelerating rate, smoothing the universe, suppressing curvature, and turning microscopic uncertainty into the seeds of galaxies. Yet the field that may have driven this expansion has never been identified, and inflation itself has never been directly observed. Where in the world are you watching or listening from, and what time is it there? Leave a comment with your city or country, especially if this is part of a quiet late-night science session. Thank you for spending some of your time with Astros Explains. If these calm journeys through difficult science are worth keeping around, a like, subscription or share helps the channel continue making them. From the uniform glow of the cosmic microwave background, the trail now leads backward toward the brief expansion that may have shaped everything that followed. The Hot Big Bang is often mistaken for a description of an explosion, as though all matter once occupied a tiny point inside a larger and otherwise empty space, and then burst outward. That picture is convenient, but it is not what the standard cosmological model actually says. The Big Bang framework describes a universe whose large-scale fabric was once much hotter, denser, and more compact than it is now, with space itself expanding as time passed. In that account, there is no ordinary center from which everything flies away, and there is no surrounding emptiness into which the universe expands. The expansion belongs to the geometry of space-time. Distances between widely separated regions grow because the scale of space changes. When that expansion is run backward, the familiar universe becomes hotter and denser, eventually reaching conditions so extreme that the physics of atoms, nuclei, and even ordinary matter no longer applies in the usual way. This backward reconstruction is powerful, but it does not automatically reveal an absolute beginning. It tells a reliable story only as far as the tested laws and models remain trustworthy. Beyond that boundary, the equations may continue to be written down, but the confidence attached to them changes. The distinction matters because cosmic inflation is often placed very early in this history, before the ordinary Hot Big Bang phase, yet inflation itself is not known to be the first event, nor is it known to emerge from nothing. It is better understood as a proposed dynamical episode in an already evolving early universe, one that may explain why the later hot universe began in such an unusually smooth and orderly state. The Hot Big Bang model is exceptionally successful once certain early conditions are supplied. It explains how an expanding plasma cools, how protons and neutrons can combine into the first light nuclei, how electrons eventually bind to nuclei to form neutral atoms, and how radiation then travels freely enough to leave behind the cosmic microwave background. It also fits naturally into the later history in which gravity gathers matter into galaxies' clusters and larger structures. But these successes begin with a set of conditions already in place. The early universe has to be very nearly uniform over enormous scales. Its spatial curvature has to be remarkably small. The fluctuations from place to place have to be tiny, but not exactly zero, because a perfectly smooth universe would have no seeds from which galaxies could later grow. The Hot Big Bang model can evolve those conditions forward with great precision, yet in its simplest non-inflationary form it does not explain why those particular conditions were there to begin with. This is the opening in which inflation enters. Inflation does not replace the Hot Big Bang. It changes what may have happened immediately before the hot phase became established. During inflation, the scale of the universe is proposed to have increased at an accelerating rate for a brief interval. If that interval occurred, then a small region that was once physically connected could have been stretched to become vastly larger than the region visible today. Features that seem oddly coordinated across the modern sky might then share a common causal past. Spatial curvature that might once have been significant could be driven toward apparent flatness over the observable region. unwanted relics left from still earlier high-energy physics could be diluted until they became extraordinarily rare. Even more important minute quantum fluctuations present during inflation could be stretched outward and later become the starting pattern for cosmic structure. These are not separate decorative benefits added after the idea was invented. They are part of the reason inflation became such a central framework in modern cosmology. Yet none of them turns inflation into a complete account of the beginning. The phrase before inflation remains scientifically uncomfortable because the answer depends on a theory that does not yet exist in settled form. General relativity describes gravity on large scales with extraordinary success, but when the universe is pushed backward towards sufficiently extreme density and energy, quantum effects should become essential. A theory that fully unites gravity with quantum physics has not been experimentally established. Inflation is usually modeled using quantum fields within an expanding spacetime, but that description may itself rest on deeper physics that is still unknown. The origin of the inflationary state therefore remains open. Perhaps inflation began after some earlier non-inflationary phase. Perhaps it emerged from conditions shaped by quantum gravity. Perhaps the universe passed through a bounce from an earlier contracting state. Perhaps the relevant description looks nothing like any of these possibilities. Each proposal carries assumptions, and none has earned the status of a confirmed prehistory. Even the idea of a singular beginning has to be handled carefully. When classical general relativity is extrapolated backward under broad conditions, it can lead to singular behavior in which quantities such as density or curvature cease to remain finite. A singularity in an equation is not automatically a photograph of a physical event. It can instead mark the point where the mathematical description being used has reached the edge of its validity. For that reason, the oldest moments accessible to cosmology are not best treated as a known first instant followed by a fully mapped sequence. They are better treated as a narrowing corridor of increasingly uncertain inference. The hot Big Bang occupies the well-supported part of that corridor. Inflation may extend the story deeper. Whatever comes before inflation lies deeper still. This ordering also clarifies why inflation should not be described as the explosion that made the universe. Inflation is a period of accelerated expansion, not an explosion of material through pre-existing space. Nor should its end be confused with the later appearance of stars, galaxies, or even atoms. In most inflationary scenarios, the end of inflation is followed by a process in which the energy associated with the inflationary dynamics is transferred into particles and radiation. That transition, broadly called reheating, establishes the hot conditions from which the conventional Big Bang evolution proceeds. In this sense, the phrase hot Big Bang refers to the thermal state after inflation, rather than necessarily to the ultimate origin of everything. This framing leaves a subtle but important gap. Inflation may explain why a large region becomes smooth, flat, and seeded with nearly scale-invariant fluctuations, but it still has to begin somewhere in the space of possible conditions. Different models make different assumptions about that starting point. Some can operate across a broad range of initial states. Others appear to require more specific circumstances. Some versions lead naturally toward eternal inflation, in which inflation ends in some regions while continuing in others. Other approaches try to avoid that picture. None of these possibilities has been established as the unique history of the cosmos. The early universe therefore remains divided into layers of confidence. There is a later thermal history supported by multiple observations. There is an inflationary framework that explains several otherwise puzzling features and makes predictions that can be tested against the cosmic microwave background and large-scale structure. And there is a still earlier domain where the evidence becomes thinner and the theoretical choices multiply. That layered structure is more faithful to the science than a single dramatic origin story. It allows inflation to be important without asking it to answer questions that it has not yet answered. The deepest value of the idea is not that it closes the beginning, but that it moves the boundary between explanation and assumption. Conditions that once had to be inserted by hand can, under inflation, emerge from a physical process. Yet that process inherits its own questions. What set it in motion? What field or mechanism carried it? Why its energy had the required form? Whether it began everywhere or only in a region? Whether there was a meaningful earlier phase at all? These questions do not weaken the later successes of cosmology. They define the frontier at which those successes stop. And from that frontier, the first puzzle is already visible. The universe that emerges into the hot Big Bang appears extraordinarily uniform across regions that, without an earlier accelerated expansion, seem too far apart ever to have coordinated their temperatures. That apparent contradiction is where the horizon problem begins. The cosmic microwave background does not look perfectly smooth, but its departures from smoothness are extremely small, and that fact carries an old difficulty for the standard hot Big Bang picture. This radiation fills the sky as a faint thermal afterglow from a time when the universe had cooled enough for electrons and atomic nuclei to combine into neutral atoms, allowing light to travel freely across space. By then, the universe was already hundreds of thousands of years old, yet the temperature of this radiation is almost the same in every direction. Tiny variations exist, and those variations are essential, because they later help trace the beginnings of cosmic structure, but the overall uniformity is striking. Regions separated by enormous distances on the sky appear to have reached nearly the same temperature. In ordinary thermal physics, matching temperatures usually suggest some earlier opportunity for interaction. Hotter regions exchange energy with cooler ones until differences are reduced. But when the expansion history of the universe is calculated without an inflationary stage, many widely separated parts of the cosmic microwave background appear never to have had enough time to communicate before the radiation was released. Light, heat, or any other causal influence could not have crossed the distance between them. Their similarity therefore seems difficult to explain. This is the horizon problem. The word horizon here does not describe an edge of the universe. It refers to a limit on causal contact. Because signals cannot move locally faster than light, any region of the universe has only a finite distance over which information could have travelled since an earlier time. That distance defines a causal horizon. If two regions lie outside one another's causal horizons, then no ordinary physical process could have coordinated conditions between them during the period being considered. In a simple non-inflationary hot Big Bang history, the observable universe at the time the cosmic microwave background formed contains many such regions. They are visible together across the modern sky, but their earlier light cones do not overlap far enough in the past to allow them to share a common thermal history. The puzzle is therefore not that the universe contains smooth regions. Local smoothness is easy to understand when neighbouring matter and radiation can interact. The puzzle is that the smoothness extends across scales that appear too large for local interactions to have established it. This makes the problem one of initial conditions rather than one of later evolution. The standard hot Big Bang equations can preserve an already smooth distribution, while the universe expands, but without some additional mechanism, they do not explain why regions that were never in contact began with nearly identical temperatures. One possibility would simply be to assume that the early universe started in this highly coordinated state. That is logically possible, but it leaves the uniformity unexplained. Inflation changes the geometry of the problem by changing the relationship between present distance and past causal contact. During an inflationary phase, space expands at an accelerating rate. A region that begins small enough for its contents to interact can be stretched to an enormous size. Points that are now separated by distances far greater than their earlier causal horizon need not always have been separated. Before and during the relevant part of inflation, they can originate inside a much smaller domain where physical processes have had time to establish approximately common conditions. Inflation then enlarges that domain so dramatically that pieces of it eventually become the widely separated regions visible in the cosmic microwave background. The important move is therefore not that inflation allows information to travel faster than light. It does not. Instead, it allows regions that are now remote to have been close enough in the past to share information before rapid expansion carried them apart. The distinction is central. Local physics still respects the usual causal limit. What changes is the scale of the space through which those local processes are embedded. A useful way to frame the idea is to consider the size of a causally connected patch compared with the size of the region that later becomes observable. Without inflation, the region visible today is assembled from many early patches that were never mutually connected. With sufficient inflation, the entire observable region can descend from a single, much smaller patch, or from a domain that was causally connected before its parts were stretched far beyond their original separations. The near-uniform temperature then becomes less mysterious because the conditions across the visible universe are inherited from a common earlier environment. This does not mean inflation produces exact uniformity. In fact, perfect uniformity would create its own problem, because later galaxies and clusters require small differences in density. The strength of the inflationary picture is that it can explain both broad smoothness and small departures from smoothness. The large-scale background becomes nearly homogeneous because one connected region is expanded to cosmic dimensions, while quantum fluctuations present during inflation can survive as tiny irregularities. Those irregularities are not a failure of the mechanism. They become one of its most important predicted consequences. The horizon problem is therefore not simply a complaint that the universe looks too smooth. It is a question about why it looks smooth at one level and structured at another. The cosmic microwave background has nearly uniform average temperature, yet it contains a delicate pattern of hotter and cooler spots. Inflation offers a framework in which both features can arise from the same early episode. A small region can approach thermal uniformity, then accelerated expansion can stretch that region across enormous scales, while microscopic fluctuations are simultaneously enlarged into the seeds of later structure. The result is a universe that is smooth enough to match the background radiation and uneven enough to form galaxies. This connection between causal history and observation is one reason the horizon problem became so influential in cosmology. It turns a visual feature of the sky into a question about what must have happened long before the cosmic microwave background existed. The radiation itself is much younger than inflation in this framework, yet its uniformity can preserve information about whether distant regions once shared a common origin. The later sky becomes a record of earlier geometry. Still, inflation does not answer every possible question hidden inside the horizon problem. It explains how a small connected patch can become large enough to include the observable universe, but the properties of that original patch still depend on the model. The mechanism must begin under conditions that permit inflation to occur, and different theories disagree about how natural or special those conditions are. Nor does solving the horizon problem prove that inflation happened. It shows why inflation is useful and why it has explanatory power. A successful theory must do more than remove one puzzle. It must also generate predictions that can survive comparison with data. The pattern of primordial fluctuations, the statistical properties of the cosmic microwave background, and the possible presence or absence of gravitational wave signatures all become part of that larger test. Yet the horizon problem remains the clearest entry point into the logic of inflation, because it exposes the difference between merely evolving an initial state and explaining why that initial state has the form it does. In a universe without inflation, distant regions can be assigned matching temperatures by assumption. In an inflationary universe, their similarity can emerge from a period when they were not distant at all. What appears today as coordination across impossible separations may instead be the fossil of an earlier intimacy, preserved after space expanded so rapidly that once neighbouring regions became parts of opposite skies. That idea resolves one form of apparent contradiction, but it also prepares the next. If inflation can stretch a connected region until it fills the observable cosmos, then the same expansion should also alter the role of spatial curvature. The uniformity problem leads naturally into a geometric one, where the question is no longer why distant places share a temperature, but why the universe as a whole appears so close to flat. The flatness problem begins with a deceptively simple fact about geometry. General relativity does not require the universe to be spatially flat. On sufficiently large scales, space can in principle have positive curvature, negative curvature, or curvature so small that it is effectively indistinguishable from zero. Positive curvature is often compared only loosely with the surface of a sphere, while negative curvature is sometimes compared with a saddle. Those images are imperfect because they reduce a three-dimensional geometry to familiar two-dimensional shapes, but they capture the essential idea that space itself can possess curvature. Observations of the large-scale universe indicate that this curvature is very small. Within present measurement limits, the observable cosmos is consistent with a geometry that is extremely close to flat. The puzzle is not simply that flat geometry is allowed. The puzzle is why the universe remains so close to that special condition throughout its long expansion. In a conventional hot Big Bang history without inflation, any departure from exact flatness tends to become more dynamically important as time passes. That means a universe that appears nearly flat today must have been even more finely balanced in the distant past. Running the equations backward does not remove the problem, it sharpens it. The earlier the universe is examined, the closer its density must lie to the critical value separating different curvature behaviours. This is the essence of the flatness problem. It is a question about stability. A perfectly flat universe can remain flat in the mathematical model, but a universe only slightly away from flatness does not naturally stay near that state through ordinary radiation-dominated and matter-dominated expansion. The deviation grows in relative importance. A tiny early mismatch can therefore become a substantial late difference. If the universe is still close to flat after billions of years, then without another mechanism, the initial conditions appear to require remarkable precision. The relevant quantity can be described through the relationship between the actual energy density of the universe and the critical density required for spatial flatness. When those two are equal, the large-scale spatial curvature is zero. If they differ, curvature contributes to the cosmic expansion in a way that becomes increasingly significant under ordinary decelerating expansion. The flatness problem does not require the universe to be exactly flat today. It arises because the observed closeness to flatness implies an even more extreme closeness in the early universe if no inflationary phase occurred. Such tuning may be possible as an initial condition, but it lacks an obvious explanation. Inflation changes this because accelerated expansion drives the curvature contribution toward insignificance. During inflation, the scale factor grows extraordinarily rapidly, while the characteristic curvature scale is stretched along with space. Any pre-existing curvature becomes spread over a much larger region. A small observable patch then behaves increasingly like a flat piece of a surface whose full curvature exists only across a far greater scale. The common analogy is a tiny region on the surface of an enormous sphere. A small enough patch can look almost perfectly flat, even though the complete sphere is curved. Inflation applies a related geometric effect to the universe, though the underlying mathematics is not simply the geometry of a literal sphere expanding into something outside itself. There is no need for an external space. The point is that accelerated expansion increases the radius of curvature relative to the portion of the universe that can be observed. As inflation continues, the visible region becomes less sensitive to whatever large-scale curvature may have existed before. The effect is powerful because it is dynamical rather than merely descriptive. Instead of assuming that curvature began extremely close to zero, inflation can take a wider range of earlier conditions and push the observable region toward apparent flatness. In that sense, inflation does for geometry something similar to what it does for the horizon problem. It converts an otherwise delicate initial condition into the outcome of a physical process. The analogy is not exact, but the logic is related. The horizon problem asks why distant regions share nearly the same thermal properties. Inflation answers by placing those regions in a common earlier causal domain. The flatness problem asks why spatial curvature remains so small. Inflation answers by stretching the curvature scale until the observable region becomes nearly indistinguishable from flat space. Both problems arise because the ordinary hot Big Bang model evolves conditions forward very successfully, but does not by itself explain why the initial state was so special. Inflation changes the prehistory of those conditions. The degree of flattening depends on how long inflation lasts, and on the details of what happens afterward. If inflation continues for enough expansion, the curvature term is suppressed to such a degree that later cosmic history can proceed for a very long time without bringing it back to prominence. This is one reason cosmologists often discuss the duration of inflation not in seconds, but in folds, a measure of how many exponential factors the scale of the universe grows by. The exact number required is model dependent because the later thermal history also matters, but the qualitative result is robust across many inflationary scenarios. More accelerated expansion generally means stronger dilution of curvature. There is, however, an important subtlety. Inflation does not prove that the entire universe is globally flat. It can make the observable portion extremely close to flat, even if the geometry on scales far beyond observation is different. Measurements are always confined to a finite cosmic volume. When cosmologists say that the universe is consistent with spatial flatness, the statement refers to the geometry that can be inferred from observations within the accessible region and within measurement uncertainty. Inflation naturally explains why that region could look so flat without requiring the global universe to be exactly Euclidean everywhere. The distinction matters because observable flatness and absolute global geometry are not identical claims. A universe can be so gently curved that no present experiment can detect the difference across the region visible today. Inflation makes such a situation natural by enlarging the curvature radius far beyond the observable scale. The cosmic microwave background provides one of the clearest ways to test this geometry. The angular size of characteristic patterns in that radiation depends on how light has traveled through the expanding universe, and that journey is sensitive to spatial curvature. Measurements of the microwave background combined with other distance information, such as baryon acoustic oscillations, are consistent with a universe very close to spatially flat. This agreement does not establish inflation by itself because more than one theoretical framework can in principle produce near-flat geometry, and observational consistency is not the same as a direct detection of the mechanism. But it strengthens the case that any successful account of the early universe must explain why curvature is so small. Inflation provides a particularly simple dynamical route. It also reveals a broader theme that runs through early cosmology. Quantities that seem ordinary today can be highly non-trivial when traced backward. A nearly uniform temperature looks unsurprising until causal contact is calculated. A nearly flat geometry looks unsurprising until its instability under non-inflationary expansion is followed into the past. The modern universe can therefore hide the delicacy of the conditions from which it emerged. Inflation tries to remove some of that delicacy by allowing rapid expansion to erase the visible influence of earlier irregularities and curvature. Yet the mechanism cannot erase every possible relic of earlier physics in the same way. Some hypothetical objects produced at extremely high energies create another kind of problem. Instead of affecting geometry, they would survive as physical remnants whose abundance could overwhelm the later universe. The same rapid expansion that flattens space offers a way to dilute those relics almost beyond reach. This shift from a tuned starting value to an evolving physical explanation is the main reason the flatness problem became so important to the inflationary picture. The question is not whether flat space is mathematically possible. It plainly is. The question is why the observed universe should occupy such a narrow geometric range after such a long history of expansion. Inflation answers by making that narrow range an attractor-like outcome for the observable patch while leaving open the deeper question of what conditions allowed inflation itself to begin. Long before inflation was discussed as a solution to the smoothness and flatness of the universe, another problem had begun to emerge from attempts to connect cosmology with high-energy particle physics. The problem did not come from something astronomers had observed in abundance. It came from objects that theory suggested might have been produced in the early universe, but that the later universe appeared not to contain in anything like the expected numbers. Among the best known of these hypothetical relics are magnetic monopoles. Ordinary magnets always appear with two poles conventionally described as north and south, and cutting a magnet in half does not isolate either one. Each fragment becomes another magnet with both poles. Some theories that attempt to unify the fundamental interactions at very high energies, however, allow for stable objects carrying an isolated magnetic charge. Such objects would be extremely massive compared with ordinary particles and could have formed during phase transitions as the young universe cooled. If they were created efficiently and remained stable, they could survive for very long periods. That survival creates the difficulty. A relic does not need to dominate the universe immediately in order to become troublesome later. Different forms of energy dilute at different rates as space expands. Radiation loses energy, both because its number density decreases and because each photon is stretched to a longer wavelength. Non-relativistic matter loses density more slowly because its particles are simply spread through a larger volume while their rest mass remains. Very massive stable relics would behave much like matter. If a sufficiently large population of them existed early on, their density could eventually become far more important than the radiation surrounding them. The universe would then evolve in a way that conflicts with the observed thermal history and with the amount of matter inferred from later cosmology. The tension is therefore not simply that magnetic monopoles have not been seen. The deeper issue is that some otherwise attractive theories of early particle physics can produce far too many of them unless something alters their abundance. This was one of the historical settings in which inflation became compelling. Alan Guth developed an early inflationary model while studying the cosmological consequences of grand unified theories frameworks that attempt to describe several fundamental forces as different aspects of a single interaction at sufficiently high energy. Phase transitions in such theories could leave defects behind, including monopoles. A rapid period of accelerated expansion offered a striking way to address the problem. If relics already existed before inflation, their number would not necessarily have to change. Instead, the volume containing them would increase extraordinarily quickly. The same small collection of objects would be spread across an enormously larger region, driving their average density downward. In this sense, inflation acts as a dilution mechanism. It does not have to destroy a relic in order to make that relic cosmologically irrelevant. It can simply separate the relics from one another so dramatically that the probability of finding one inside the observable universe becomes extremely small. The logic is closely related to the way inflation suppresses curvature, but the physical quantity being diluted is different. Spatial curvature becomes less important because the characteristic curvature scale is stretched. A population of massive objects becomes less important because the physical volume grows, while the number of objects inside a comoving region does not increase enough to compensate. Accelerated expansion is unusually efficient at this. During a sufficiently long inflationary episode, the volume of a region rises by an enormous factor. Any pre-existing population whose number does not grow comparably is left with an exponentially reduced density. A universe that begins with many unwanted relics can therefore emerge from inflation with almost none inside the region that later becomes observable. This helps explain why the relic problem is more than an isolated historical curiosity. It shows how one dynamical process can simultaneously alter several apparently unrelated features of the early universe. Inflation can stretch causal regions, suppress curvature, and dilute heavy relics because all three effects arise from the same rapid growth of the scale factor. What looks like three separate solutions is at a deeper level one geometric change acting on three different kinds of initial condition. Yet this also reveals a limitation. Inflation can dilute relics that exist before or during the appropriate stage of expansion, but it cannot automatically remove objects produced afterward. If the universe reheats to a temperature high enough to recreate the same unwanted particles or defects, the problem can return. The details therefore depend on the particle physics of reheating and on the energy scale at which the relics form. A successful inflationary history has to be consistent not only with enough expansion, but also with what happens when inflation ends. The thermal environment that follows must not simply regenerate the population that inflation erased. This dependence ties the relic problem to later questions about how inflation transfers its energy into particles and radiation. Magnetic monopoles are also only one example of a broader class of possible remnants. High-energy theories can produce other topological defects, structures that form when a field chooses different states in different regions during a phase transition. Depending on the theory, these may include cosmic strings, domain walls, or more complicated configurations. Their cosmological effects are not all the same. Some may be compatible with observation if their abundance and energy scale are sufficiently small. Others could become disastrous if they contribute too much energy or disturb the uniformity of the universe too strongly. Inflation changes their expected abundance according to when they form. Defects produced before sufficient inflation can be stretched away from one another. Defects produced near the end of inflation or afterward may remain potentially observable. For this reason, the simple statement that inflation removes all relics would be too broad. It removes or strongly suppresses relics under particular conditions, and those conditions depend on the sequence of events in the early universe. The original monopole problem, nevertheless, had unusual importance because it connected an abstract idea about particle unification with a direct cosmological consequence. A theory could look elegant at the level of fundamental interactions and still create an unacceptable universe. Cosmology therefore became a filter on high-energy physics. The early universe was not merely a stage on which particle theories operated. It was a test of whether their predicted remnants could survive into a cosmos resembling the one observed. Inflation offered a way to relax that conflict without abandoning the underlying high-energy ideas completely. If a grand unified transition occurred before the main period of inflation, the monopoles it produced could be dispersed so widely that none might lie within the observable region today. Their absence would then be unsurprising rather than problematic. This solution has a different character from a direct experimental detection. No confirmed monopole population has been found that demonstrates such dilution happened, and the relevant grand unified theories themselves remain unverified. The relic problem is therefore not direct evidence for inflation. It is a theoretical consistency problem for which inflation provides a powerful remedy. That distinction is important throughout inflationary cosmology. Horizon uniformity, near flatness, and relic dilution all show how inflation can improve the explanatory structure of the early universe, but none independently proves the mechanism. Their strength lies in convergence. A single period of accelerated expansion addresses several otherwise separate puzzles, while also opening a route toward observable predictions from primordial fluctuations. The historical appeal of inflation grew because it did not merely patch one discrepancy. It reorganized the early universe in a way that changed causal contact geometry and particle abundance at once. The relic problem makes this especially clear because its solution depends almost entirely on expansion itself. No complicated destruction process is required. Space simply grows so rapidly that whatever rare heavy remnants existed become separated by distances far exceeding anything accessible later. From inside the surviving observable patch, they can effectively disappear without ever being annihilated. By this point, the recurring mechanism is beginning to take shape. The same accelerated expansion that can make distant regions share a common past and make curved space appear flat can also empty an enormous volume of unwanted primordial debris. The next question is therefore no longer what inflation can solve, but what this unusual expansion actually is in physical terms, and how space-time can enlarge so quickly without requiring matter to race through space beyond the local speed of light. Inflation is not defined by the universe becoming merely larger. The universe is already expanding in the ordinary hot Big Bang picture, and it continues to expand long after inflation has ended. What makes inflation different is the way that expansion behaves. During an inflationary phase, the cosmic scale factor grows with positive acceleration, meaning that the rate at which distances between widely separated freely moving points increase is itself increasing. In many simple models, that growth is close to exponential for a time, so each equal interval of cosmic time multiplies the scale factor by roughly the same factor rather than adding the same amount. This distinction sounds mathematical, but it changes the causal structure and geometry of the early universe in exactly the ways needed to address the horizon flatness and relic problems. Ordinary decelerating expansion can enlarge distances while still allowing the relative importance of curvature to grow, and while leaving distant regions causally disconnected. Accelerated expansion behaves differently. It can stretch a region faster than signals can cross the growing distance carry, once nearby points beyond one another's effective horizons, and dilute pre-existing contents with extraordinary efficiency. To understand this without turning inflation into an explosion, it helps to separate two kinds of distance. Cosmologists often describe matter as occupying positions that remain fixed in co-moving coordinates, while the scale factor tells how physical distances between those positions change. A galaxy that simply follows the large-scale expansion can remain at the same co-moving location even while its physical distance from another galaxy increases. The object is not necessarily moving through space in the ordinary sense. The geometry between the two locations is changing. Inflation magnifies this effect to an extreme degree. If the scale factor grows rapidly enough, 2 points that begin microscopically close, in comparison with later cosmic scales, can end up separated by distances vastly larger than the region that becomes observable. Nothing needs to fire outward from a central point, and nothing needs to push against an outer boundary. The expansion occurs everywhere within the description, because it is the spatial metric, the rule, that assigns physical distance to separations in coordinates that evolves with time. This is also why inflation does not violate special relativity, even when the physical distance between sufficiently remote points increases at an effective rate greater than the speed of light. Special relativity forbids a local object from passing another local object through space-time faster than light. It does not impose the same restriction on the rate at which the geometry of an expanding universe can increase the distance between two objects that are already far apart. The distinction is built into general relativity, where space-time itself is dynamic rather than a fixed stage. A photon always moves locally at the speed of light through its immediate region of space-time, yet the distance between the photon's origin and a sufficiently remote destination can still grow because the space along the route is expanding. In an inflationary phase, that growth can be so rapid that light initially travelling toward a distant region fails to reduce the physical separation. The region is being carried away by the changing geometry faster than the photon can make progress across the increasing distance. There is no local breaking of the light speed limit. The unusual behavior comes from comparing widely separated locations in a curved time-dependent space-time. The term accelerated expansion therefore has to be understood cosmologically rather than mechanically. It does not mean galaxies are feeling an ordinary outward force that makes them race faster and faster through pre-existing emptiness. In fact, during the era in which inflation is usually placed, galaxies do not yet exist. The relevant description concerns fields, energy and space-time on scales, and at energies far earlier than the formation of atoms or stars. What accelerates is the scale factor, a pair of idealized points that simply follows the cosmic expansion, becomes separated at an increasing rate, because the conversion between co-moving separation and physical separation changes with time. This is enough to produce the enormous stretching associated with inflation. In many textbook treatments, near exponential expansion is emphasized because it gives a simple picture of repeated multiplication. A region grows by one factor, then by a similar factor again and again, so the total increase becomes enormous even if the inflationary interval is very short by everyday standards. The exact time dependence need not be perfectly exponential, and different inflationary models produce somewhat different histories. The essential condition is accelerated expansion, sustained long enough to perform the required cosmological work. This condition also reveals why inflation is more than a name for very rapid growth. A universe could in principle expand quickly without being in an inflationary regime if the expansion was slowing rather than accelerating. The key property is the sign of the acceleration of the scale factor, because that determines how characteristic horizons and curvature scales evolve relative to the expanding background. Inflation is therefore best defined by dynamics, not by a particular speed. Another subtle point follows, because recession speed in cosmology depends on distance. Statements that some regions recede faster than light do not identify a special barrier moving through space. Nearby objects can have small recession speeds, while more distant ones have larger values under the same expansion law. During inflation, the range of distances over which effective superluminal recession occurs can become extremely important, but the local laws remain ordinary. This distance-dependent behavior is one reason everyday intuition struggles with early universe expansion. Human experience is built around objects moving inside a fixed environment. Cosmology allows the environment that defines distance itself to evolve. The same idea applies today, though much more gently than in an inflationary epoch. On sufficiently large scales, cosmic expansion increases the separation between distant galaxies, and very remote regions can have recession rates greater than the speed of light without violating relativity. Inflation is an extreme early version of this geometric behavior, with accelerated expansion dominating the dynamics for a limited period. Its effectiveness comes from what that acceleration does to scales. A small causally connected domain can be stretched beyond the size of the later observable universe. Spatial curvature can be driven to observational insignificance. Heavy relics can be diluted until their expected number within an accessible region becomes tiny. Quantum fluctuations initially associated with microscopic field behavior can be enlarged to wavelengths relevant to the formation of cosmic structure. These consequences all depend on the same central fact. Physical length scales grow extremely rapidly relative to other characteristic scales in the problem. Yet saying that space-time expands still leaves a deeper question unanswered. General relativity tells how a given distribution of energy and pressure influences cosmic expansion. So accelerated expansion requires a particular kind of stress energy. Ordinary non-relativistic matter does not provide it. Radiation does not provide it either. Both tend through their gravitational effect in the homogeneous universe to slow the expansion rather than sustain acceleration. Inflation therefore demands an unusual energy component whose pressure is sufficiently negative. In the most familiar models, that role is played by the potential energy of a scalar field. The field is hypothetical, often called the inflaton, and its slowly changing energy can behave in the way needed to keep the scale factor accelerating. This description is powerful because it converts inflation from a purely geometric statement into a physical model, but it also introduces new uncertainty. The geometry of inflation can be described with confidence as a class of solutions. The identity of the agent producing it is not known. No inflaton particle has been detected, and no unique inflationary field has been established. Cosmic inflation is therefore simultaneously simple and incomplete. Its defining behavior is clear: a temporary era of accelerated expansion in which the scale of space grows extraordinarily rapidly. Its broad consequences can be calculated, but the physical source of that behavior remains one of the central open questions, and it is there in the search for what could hold the young universe in such an unusual state that the next part of the story begins. If accelerated expansion requires an unusual form of energy, then the central physical question becomes what could provide it. General relativity does not prescribe one unique substance that must drive inflation. It relates the expansion of the universe to the energy density and pressure of whatever fills space-time, leaving particle physics to identify the actual source. Ordinary matter is not enough. Radiation is not enough. Both contribute positive energy density, but their pressure does not have the unusual character needed to maintain accelerated expansion in the early universe. In the most familiar inflationary models, the required behavior is supplied by a scalar field, a type of field described at every point in space by a single value, rather than by a direction. The hypothetical field associated with inflation is usually called the inflaton. The name is convenient, but it can give a misleading impression of certainty. No inflaton particle has been detected, as no unique inflaton field has been identified, and no experiment has established that one specific scalar field was responsible for cosmic inflation. The inflaton is best understood as a theoretical framework for describing how the energy needed for inflation might behave. Scalar fields are not strange additions to modern physics in themselves. The Higgs field is a confirmed example of a scalar field, although that does not mean the Higgs field necessarily caused inflation. What matters in an inflationary model is the way the field stores and changes energy. A scalar field can possess kinetic energy associated with how quickly its value changes, and potential energy associated with where it sits within an effective energy landscape. If the potential energy dominates strongly enough, the combined energy and pressure of the field can produce the negative pressure required for accelerated expansion. Negative pressure sounds unusual because everyday pressure is associated with particles pushing outward against a container, but cosmological pressure is a more general property of energy and matter. In general relativity, pressure itself contributes to gravity. A sufficiently negative pressure can therefore alter the evolution of the scale factor in a way that allows expansion to accelerate rather than decelerate. The field does not need to push galaxies apart, and it does not operate like a gas filling a chamber. At the epoch under discussion, there are no galaxies to push. The field contributes to the energy content of spacetime, and spacetime responds through the gravitational equations. In the simplest picture, the inflaton begins in a region of its potential, where its energy density is high and changes only gradually. As long as the field evolves slowly enough, potential energy remains dominant. The resulting pressure becomes negative enough to sustain inflation. The universe then expands rapidly while the field itself changes comparatively little. This is the foundation of slow-roll inflation, but even before that more detailed description is introduced, the broad physical logic is already visible. A nearly constant energy density behaves very differently from matter or radiation during expansion. Matter becomes more dilute as volume increases. Radiation becomes more dilute still because its wavelengths are stretched. But a field whose energy is dominated by an almost unchanged potential can maintain roughly the same energy density even while space expands. The total amount of energy associated with a larger physical volume can therefore increase without implying an ordinary violation of local energy conservation, because global energy accounting in an expanding spacetime does not behave like energy conservation in a fixed laboratory system. General relativity does not generally provide a simple, globally conserved total energy for the entire evolving universe. What remains well defined is the local conservation of energy and momentum encoded in the field equations. This allows an inflationary state to persist while the physical volume grows enormously. The exact shape of the inflaton potential is where models begin to differ. Some potentials are steep in one region and flat in another. Some contain broad plateaus where the field can evolve slowly for a long period. Others involve more complicated structures, several interacting fields, or transitions between different states. Different shapes lead to different inflationary histories, and crucially to different predictions for observable quantities such as the spectrum of primordial density fluctuations and the possible strength of primordial gravitational waves. This is why identifying the driving field is not merely a philosophical concern about what happened first. The microphysics of inflation leaves traces in the statistical structure of the later universe. A field that evolves in one way can produce a slightly different pattern of fluctuations from a field that evolves in another. Observations can therefore rule out or constrain broad classes of inflationary models even without detecting the inflaton directly. The connection is indirect but powerful. The early field influences the expansion rate. The expansion rate influences how quantum fluctuations are stretched. Those fluctuations become primordial perturbations. The perturbations later appear in the cosmic microwave background and in the distribution of matter across the universe. The sky can therefore test properties of a field that may have existed at energies far beyond anything attainable in a laboratory. Yet this does not mean every scalar field model is equally natural or equally successful. A potential must allow enough accelerated expansion, end inflation appropriately, generate perturbations consistent with observation and transfer energy into the hot particles and radiation needed for the later Big Bang history. It must also avoid producing unwanted features such as excessive fluctuations or observational signatures already excluded by data. Each requirement narrows the possibilities. Some historically important models have come under increasing pressure as measurements have improved. Others, especially models with flatter or plateau-like potentials in certain simple settings, remain compatible with current constraints. This continuing process of elimination is one reason it is misleading to speak of the inflaton as though its identity were already known. What exists is a family of possible fields and mechanisms whose consequences can be compared with observation. There are also models in which the effective agent of inflation is not a simple fundamental scalar field at all. Inflation can arise from modified gravitational dynamics, from combinations of several fields, from fields related to deeper particle theories, or from effective descriptions that behave like scalar fields even if their underlying physics is more complicated. Some scenarios connect inflation to the Higgs field under additional assumptions. Others use axion-like fields, supersymmetric constructions, extra dimensions, or geometric modifications of gravity. These possibilities are theoretically diverse, and none has received decisive experimental confirmation. The success of the inflationary idea therefore has to be separated from the uncertainty of its engine. Accelerated expansion may be well motivated as a cosmological mechanism, while the identity of what caused that expansion remains unsettled. This separation is common in physics. A phenomenon can be inferred from its effects before its microscopic explanation is complete. But in inflationary cosmology, the gap is especially large because the relevant energies and times are so remote from direct experiment. The inflaton, if it existed, may never have survived as a stable particle. Its energy could have been transferred almost entirely into other fields when inflation ended. Searching for it is therefore not necessarily like searching for a relic particle drifting through space today. Its existence may instead have to be reconstructed from the patterns it created before disappearing from the later thermal universe. That reconstruction depends on understanding how the field moved. If it changed too quickly, its kinetic energy would become important and accelerated expansion could fail. If its potential were sufficiently flat over the relevant range, the field could evolve slowly enough for inflation to continue. This gradual motion gives the next stage of the explanation its familiar name. Slow roll does not mean that anything physically rolls through space like a solid object. It describes the controlled evolution of a field through its potential landscape, where friction associated with cosmic expansion can keep the motion gentle, even while the universe itself grows at an extraordinary rate. The contrast is one of the most striking features of the inflationary picture. An almost slowly changing field can drive an almost violently changing scale factor. The proposed engine is quiet in its own evolution, while its effect on geometry is immense. That relationship turns the abstract inflaton into something calculable, because once the potential and the field dynamics are specified, the duration of inflation, the rate of expansion, and the primordial fluctuations can all be worked out. The next question is therefore not simply whether a scalar field could drive inflation, but under what conditions it can remain in the right state long enough to do so. Slow-roll inflation sounds at first like a contradiction. Inflation describes an era in which the scale of the universe can increase with extraordinary speed, yet the field proposed to drive that expansion is said to roll slowly. The contrast disappears once the two motions are separated. The rapid change belongs to the scale factor of the universe. The slow change belongs to the value of the inflaton field as it moves through its potential energy landscape. In the simplest models, that landscape is represented by a function that assigns a potential energy to each possible value of the field. The familiar analogy is a ball moving down a hill, but the analogy has to be handled carefully. The inflaton is not a small object traveling through ordinary space, and its potential is not a literal surface. It is a field whose value changes everywhere across a sufficiently uniform region, while the shape of the potential determines how strongly the field is driven to evolve. If the potential is steep, the field tends to change rapidly. If the potential is broad and flat enough, the field can evolve much more gently. That gentle evolution is the central condition behind slow roll. The reason it matters is that the energy associated with the field has two main parts. One is kinetic, linked to how quickly the field changes with time. The other is potential, linked to where the field sits on its energy curve. Inflation is easiest to sustain when the potential part dominates. Under those conditions, the field behaves approximately like a nearly constant energy density with strongly negative pressure, and that combination allows the expansion of the universe to accelerate. If the field begins to move too quickly, kinetic energy becomes more important, and the inflationary state weakens. Slow roll therefore describes a regime in which the field is moving but not so quickly that it gives up the potential energy dominance required for accelerated expansion. Cosmic expansion itself helps maintain this regime. In the equation governing the motion of a scalar field, there is a term often described as Hubble friction. It is not friction in the ordinary mechanical sense, and no energy is being lost to a physical medium. Instead, the expansion of the universe resists rapid changes in the field value. When the expansion rate is high, this damping effect can be strong enough to keep the field moving gradually, even if the potential is not perfectly flat. The field is pulled by the slope of its potential, while the expansion continually suppresses its motion. Slow roll emerges when those influences settle into a balance in which the field drifts rather than races. This is why the ball on a hill picture, though imperfect, can still be useful. A ball descending a gentle slope through a highly resistive environment would move slowly even while losing potential energy. The inflaton is not encountering a substance, but the expanding background plays an analogous mathematical role by damping the evolution of the field. The flatter the relevant part of the potential, and the stronger the expansion, the easier it is for potential energy to remain dominant over a sustained interval. Cosmologists describe this condition using quantities called slow roll parameters. These parameters measure in different ways how steep the potential is and how quickly its slope changes compared with the overall energy scale. When the parameters are small, the potential is flat enough for slow roll inflation to be a good approximation. The exact definitions vary depending on whether they are written in terms of the potential or the expansion rate, but their purpose is similar. They provide a compact way to ask whether the field is evolving gradually enough to maintain accelerated expansion, and whether the expansion itself is changing slowly from one moment to the next. A slow roll model is therefore not simply a picture, it is a calculable regime with conditions that can be tested inside a given theory. If a proposed potential is too steep, slow roll may never begin. If it is flat enough only over a narrow interval, inflation may not last long enough. If it is too flat for too long, the exit from inflation can become difficult, or the predicted pattern of fluctuations can disagree with observation. The potential has to perform several tasks at once. It must sustain accelerated expansion, allow the field to evolve, generate the right primordial perturbations, and eventually release the universe from inflation. This last requirement is essential because an inflationary phase that never ends in the region that becomes observable would not produce the hot cosmic history that follows. Slow roll, therefore, contains its own ending. As the field moves through its potential, it may reach a region where the slope becomes steeper, or where the potential energy falls enough that kinetic effects can no longer be neglected. The slow roll parameters then grow, the approximation begins to fail, and accelerated expansion comes to an end. In some models, this transition is smooth, with the field gradually speeding up. In others, the termination can involve additional fields or instabilities. Slow roll inflation is a broad framework rather than a single unique script for how the universe must behave. Even within the simplest single field versions, different potential shapes generate different histories. A broad plateau can keep the field moving gently for a long period. A simple curved potential can produce a different rate of evolution. A potential with features bends or changes in slope can leave corresponding signatures in the primordial perturbations. This connection between the potential and observable structure is one of the most important reasons slow roll matters. The background expansion and the field evolution are not hidden from observation in a completely inaccessible way. Quantum fluctuations generated during inflation depend on the expansion rate and on how the field is changing. Those fluctuations later become density and curvature perturbations, whose statistical properties can be measured in the cosmic microwave background and large-scale structure. In that sense, the potential acts like an ancient control surface, whose shape can influence patterns still visible in the sky. The connection is indirect, and several different potentials can produce very similar predictions, but it allows observation to narrow the space of possibilities. Slow-roll models often predict a primordial spectrum that is close to scale, invariant, meaning fluctuations have nearly the same statistical strength across a wide range of scales after the appropriate cosmological factors are taken into account. The spectrum is not expected to be perfectly scale invariant in many realistic models. This slight deviation contains information about how slowly the inflationary conditions were changing. This is one reason the measured spectral tilt in the cosmic microwave background is so important. It does not identify a unique inflaton potential, but it tests whether broad classes of slow-roll behavior are compatible with the data. The same dynamics can also influence the expected strength of tensor perturbations, the primordial gravitational waves that inflation may generate. A field moving through one type of potential can predict a relatively large tensor signal, while another can predict one so small that it remains beyond present sensitivity. Slow roll is therefore not merely a convenient way to produce enough expansion. It is a bridge from the hypothetical microphysics of an early field to measurable cosmic statistics. Even so, the approximation should not be mistaken for a law that all inflationary models must obey. Inflation can be constructed in regimes where slow roll is temporarily violated, where several fields interact, where the field motion follows a more complicated path, or where the underlying mechanism is not well described by a single canonical scalar field at all. Some departures from slow roll can produce distinctive features or enhanced non-Gaussianity in the primordial fluctuations. Others are used to address theoretical questions about how inflation begins or ends. The popularity of slow roll comes from its simplicity and from the fact that it generates a broad set of predictions compatible with important observations, not from proof that nature selected this exact mechanism. It remains a framework within a larger family of inflationary ideas. Still, it provides the clearest way to understand how an almost steady source of energy can drive an immense change in geometry. The field need not plunge rapidly down its potential. It can move only a little while the scale factor multiplies again and again. Each interval of slow evolution gives the universe another interval of accelerated expansion. The cumulative growth is therefore determined not only by how fast the universe is expanding, but by how long the field can remain in the slow-roll regime. Cosmologists capture that cumulative history through E folds a measure that counts repeated multiplicative growth of the scale factor rather than ordinary additions of distance. Once slow roll is understood, the next question becomes quantitative in a new way. It is not enough to say that inflation happened rapidly. The issue is how much inflation occurred before the field left the flat part of its potential, and how many rounds of exponential-like growth were needed to turn one small early region into the immense domain from which the observable universe emerged. Inflation becomes easier to misunderstand when its size is described only with ordinary multiplication. Saying that the universe expanded by an enormous factor is true, but it hides the way cosmologists actually track such growth. The preferred measure is the E-fold. One E-fold means that the cosmic scale factor increases by a factor equal to the mathematical constant called E, a number, a little larger than 2.5. After another E-fold, the scale factor is multiplied by the same factor again. The growth is therefore cumulative and multiplicative rather than additive. A few E-folds already produce a noticeable increase. Many E-folds produce an expansion so large that ordinary intuition quickly becomes unreliable. This is why inflation can transform a region that begins extremely small into one large enough to contain everything later visible in the observable universe. The importance of the E-fold is not that nature must count expansion in discrete steps. Inflation is continuous. The measure is simply a convenient way to describe how much the scale factor changes during that continuous process. It is especially useful when the expansion is close to exponential, because equal intervals in the appropriate inflationary evolution can correspond to similar multiplicative increases in size. Instead of carrying an unwieldy expansion factor through every calculation, cosmologists can describe the same history by stating how many e-folds occurred between two moments. The larger the number, the greater the total stretching. Yet the number itself should not be treated as a directly observed quantity written into the sky. No instrument has watched inflation unfold and counted its e-folds one by one. The required amount is inferred from what inflation is expected to accomplish, and from the history assumed to follow it. To solve the horizon problem, inflation must last long enough for a region that was once causally connected to be stretched beyond the scale of the observable universe. To suppress spatial curvature, it must continue long enough for curvature to become negligible across that region. To dilute unwanted relics, it must enlarge volume enough that any pre-existing population becomes exceedingly sparse. These demands all point toward substantial expansion, but they do not by themselves select one universal number. Many simple scenarios are often described as requiring on the order of several dozen e-folds, and values around a few tens beyond 50 frequently appear in discussions of the scales visible today. But the exact requirement depends on details that occur both during and after inflation. This dependence is crucial. The relationship between a scale observed in the modern universe and the moment when that scale was stretched during inflation cannot be reconstructed from inflation alone. It also depends on the energy scale of inflation, on how inflation ends, on how reheating proceeds, and on the later periods dominated by radiation and matter. If reheating is rapid and reaches a high temperature, the mapping between inflationary scales and present scales differs from the case in which reheating is prolonged or inefficient. A change in the post-inflationary thermal history can therefore shift the estimated number of e-folds associated with the portion of inflation relevant to present observations. This is why a figure such as 60 e-folds should be understood as a useful benchmark in many models, rather than as a measured cosmic constant. The distinction becomes clearer by separating the total duration of inflation from the smaller interval directly connected to observable scales. Inflation could in principle have lasted much longer than the minimum needed to solve the classic problems. The observable universe would then represent only a limited part of the region produced by the full inflationary episode. What matters for observations such as the cosmic microwave background is often the number of e-folds between the time a particular cosmological scale left the relevant horizon during inflation and the time inflation ended. Different scales leave at different moments. Large scales associated with broad patterns in the cosmic microwave background leave earlier, while smaller scales leave later. The statistical properties of their fluctuations therefore carry information about how the inflationary background was changing across this interval. Counting e-folds is thus not only a way to measure total growth, it also becomes a clock for inflationary dynamics. Instead of asking what second of inflation a fluctuation belongs to a model, can ask how many e-folds remain before inflation ends. This is useful because the absolute duration in seconds depends strongly on the inflationary energy scale, while the change in the scale factor directly captures the geometric effect inflation is meant to produce. A very short physical time can contain enormous expansion if the expansion rate is sufficiently high. That combination is one of the reasons everyday language struggles with inflation. Short duration normally suggests small change, but exponential, like growth, does not obey that intuition. The relevant quantity is not how long inflation feels by ordinary standards, but how many multiplicative cycles of expansion fit within that interval. Each e-fold compounds the previous one. After enough of them, a length that once belonged to microscopic physics can correspond to an astronomical or even cosmological scale later on. The same compounding acts on volume even more strongly because volume grows with the cube of length. A modest-looking increase in the number of E-folds can therefore create an extraordinary increase in physical volume. This explains why relic dilution is so effective, and why one initially small patch can come to dominate the later observable region. The expansion does not have to erase every initial feature by direct interaction. It can simply enlarge one smooth patch so much that other regions are carried far outside the domain that becomes visible. There is also a caution hidden inside this success. If inflation lasts only barely long enough, some traces of pre-inflationary conditions might in principle remain closer to observable scales. If it lasts much longer, the visible universe can become almost completely insensitive to those earlier conditions. The amount of inflation therefore influences how much information about the pre-inflationary state could survive into later observables. In many models, sufficient inflation acts like a powerful filter, leaving the observable universe dominated by the state generated during the inflationary phase rather than by whatever came before. This filtering is part of the explanatory attraction of inflation, but it also makes the earliest history harder to reconstruct. The more effectively inflation solves the initial condition problems, the more thoroughly it can conceal the conditions that preceded it. The count of E-folds therefore connects two opposite ideas. More inflation increases the ability of the theory to produce a smooth, flat relic, poor observable universe, yet it can also push earlier information farther beyond reach. This does not mean that every additional E-fold is observationally identical. The fluctuations generated during the interval relevant to observable scales can still contain information about the field dynamics. But conditions much earlier than that interval may leave little accessible trace. In this way, the mathematical convenience of E-folds becomes tied to an epistemic boundary. It measures expansion, but it also measures how strongly inflation separates the visible universe from its deeper past. Once enough expansion has occurred, the next question is no longer how large the universe became. The more important question is what was being stretched along with it. A nearly uniform background field is not perfectly featureless at the quantum level. Tiny fluctuations are unavoidable in quantum fields, and during inflation the rapidly growing scale factor can carry those microscopic variations outward to enormous wavelengths. The counting of E-folds therefore leads directly from geometry into quantum physics. It tells how long there is for tiny fluctuations to be enlarged when different scales leave the inflationary horizon, and how the seeds of later structure are distributed across the cosmos. The vastness produced by inflation is not empty of information. Hidden within that expansion are small irregularities that will eventually become the pattern from which galaxies grow. Quantum fluctuations enter the inflationary story because a field in the early universe is never perfectly still in the classical sense. Even when a quantum field occupies its lowest energy state, the vacuum is not an empty background in which every physical quantity has one exact value at every moment. Quantum theory allows unavoidable fluctuations, small variations associated with the probabilistic nature of the field itself. In an ordinary setting, these variations remain microscopic and are often averaged away when larger scales are considered. During inflation, however, the geometry of the universe changes so quickly that some of these tiny variations are stretched far beyond the scales on which they began. What starts as quantum behavior can therefore become connected to structures that later span galaxies and clusters. This is one of the most remarkable features of inflation, because it creates a bridge between physics at extremely small scales and the largest visible patterns in the universe. The basic process can be understood without treating quantum fluctuations as little particles appearing and disappearing in empty space. That common picture is only a loose metaphor. A more useful description is that the value of a quantum field cannot remain perfectly definite across all scales. Different wavelengths of variation are present in the field, and during inflation the physical wavelength associated with each mode grows as the scale factor grows. A fluctuation that begins with a very short physical wavelength can therefore be stretched until its wavelength becomes comparable with a characteristic scale set by the expansion rate. Once it grows beyond that scale, its later evolution changes. The fluctuation can no longer behave in the same oscillatory way it did when its wavelength was much smaller than the expansion scale. Its amplitude becomes approximately frozen for a period, preserving information about the quantum state at the time it crossed that threshold. The language often used for this event is horizon crossing, though the terminology can be subtle. What matters physically is that the wavelength becomes larger than the characteristic Hubble scale during inflation. The fluctuation has not escaped the universe, and no object has crossed a material boundary. Instead, the expansion becomes so rapid relative to the wavelength that different parts of the fluctuation can no longer remain in ordinary causal communication on that scale. The mode is carried outward by inflation and becomes part of the large-scale pattern of the universe. Later, after inflation ends and the cosmic expansion changes character, the relevant scale can eventually become smaller than the horizon again. The perturbation then re-enters the regime where causal processes can act across it. By that time, however, the fluctuation is no longer merely a microscopic quantum variation. It has become encoded as a primordial perturbation in the density and curvature of the expanding universe. In simple inflationary models, fluctuations in the inflaton field are particularly important because small differences in the field value can correspond to small differences in when inflation ends from place to place. A region in which inflation lasts slightly longer expands slightly more. A neighboring region in which it ends slightly earlier expands slightly less. These tiny differences become variations in the curvature of spacetime and later appear as slight differences in density. The process does not create dramatic clumps during inflation. The deviations are extremely small. That smallness is essential. If the primordial universe were too irregular, later structure would become far more violent, and the cosmic microwave background would not display the delicate temperature variations that are observed. If it were perfectly smooth, however, there would be no initial pattern for gravity to amplify into galaxies. Inflation provides a mechanism that naturally produces something between those extremes, a universe that is broadly uniform but carries faint primordial irregularities. The statistical character of those irregularities is one of the most important links between inflationary theory and observation. In many simple slow-roll models, fluctuations are produced with nearly the same strength across a broad range of scales after their scale dependence is described appropriately. This behavior is called nearly scale invariant. It does not mean that every fluctuation is identical, or that the universe looks the same at every scale in a literal sense. It means that the primordial spectrum changes only gradually with scale, rather than strongly favoring one particular size. That prediction emerged as one of the major successes of the inflationary framework because observations of the cosmic microwave background show a primordial spectrum close to this form. The agreement is not exact scale invariance, and that slight departure matters. It contains information about how the inflationary expansion rate and the field dynamics were changing while observable modes were being stretched. Quantum fluctuations therefore do more than provide vague seeds for structure. Their detailed spectrum can test the behavior of the inflationary background. Another important feature is that these fluctuations are expected to be close to Gaussian in many simple models. A Gaussian distribution is one in which the statistical properties are largely captured by an average, and a variance with extreme deviations becoming progressively rarer in a characteristic way. The observed primordial fluctuations are indeed close to Gaussian, though cosmologists continue to search carefully for small departures known as non-Gaussianity. Such departures could reveal interactions, additional fields, or more complicated inflationary dynamics. A strong detection of certain forms of non-Gaussianity could therefore challenge the simplest single-field, slow-roll models, even if inflation as a broader framework remained viable. The quantum origin of perturbations is also where the distinction between classical and quantum descriptions becomes unusually interesting. The fluctuations begin as quantum states, yet the later universe can be described using effectively classical variations in density and curvature. Inflation stretches the modes and strongly suppresses some aspects of their quantum evolution, making them behave more and more like a classical stochastic pattern for many practical purposes. The deeper details of how a definite classical universe emerges from an underlying quantum state remain connected to broader questions in quantum theory, but cosmological calculations can successfully predict the statistical properties of the perturbations without requiring a complete solution to every foundational issue. The result is an early pattern that can be treated as a random field with precisely calculable correlations. These correlations become the starting conditions for everything that happens later. Inflation may also generate quantum fluctuations in the gravitational field itself. Those tensor fluctuations correspond to primordial gravitational waves, ripples in space-time that are distinct from the scalar perturbations responsible for most density structure. Their possible observational imprint will become important later, especially in the polarization of the cosmic microwave background. For the moment, the crucial point is that inflation does not merely stretch matter already present. It stretches the quantum fluctuations of fields and space-time as well. The expansion acts like an enormous amplifier of scale, not necessarily of raw amplitude, carrying microscopic variations into domains where gravity can eventually use them as a structural blueprint. This amplification does not mean that inflation invents arbitrary patterns. The statistics depend on the quantum state, the expansion rate, the field content, and the details of the inflationary dynamics. Different models therefore predict different spectral tilts, tensor strengths, correlations, and possible non-Gaussian features. The sky preserves only an indirect record, but that record is unusually valuable because it reaches back far earlier than any ordinary light signal could travel. The cosmic microwave background was emitted long after inflation ended, yet the fluctuations within it can trace their origin to quantum processes operating during inflation. The observable universe thus contains a kind of transformed quantum memory. It is not a photograph of the inflaton or a direct image of the inflationary epoch. It is a statistical fossil whose structure can be compared with theoretical predictions. This is why the quantum fluctuation mechanism moves inflation beyond the role of a solution to old cosmological puzzles. Horizon uniformity near flatness and relic dilution show what rapid expansion can repair. Primordial fluctuations show what inflation can generate. A theory becomes more scientifically useful when it not only removes difficulties but also produces new patterns that observations can test. In this case, the generated pattern is subtle enough to appear as tiny temperature and polarization variations in the microwave background, yet consequential enough to shape the entire later distribution of matter. Once inflation ends, those slight differences do not remain passive. Regions with slightly higher density exert slightly stronger gravitational attraction. Dark matter begins to collect more efficiently there. Gas later follows the growing gravitational wells. Over immense stretches of cosmic time, differences that began at the level of primordial perturbations are amplified into halos, filaments, clusters, stars, and galaxies. The next transition in the story is therefore not another change in the inflationary mechanism itself. It is the long gravitational unfolding of the pattern inflation leaves behind when quantum-scale irregularities begin their transformation into the visible architecture of the universe. The primordial fluctuations left by inflation begin as almost imperceptible differences far too small to resemble galaxies' clusters or any familiar cosmic structure. Their importance comes from what gravity does with them once inflation is over and the universe enters the hot Big Bang phase. A region whose density is slightly above the average contains slightly more gravitational attraction than its surroundings. The difference is tiny, but it does not remain irrelevant. As the universe expands and cools, gravity continually acts on these small variations, slowly encouraging matter to gather more efficiently in the denser regions. At first, the process is strongly influenced by the composition of the young universe. Radiation dominates the energy budget at early times, and ordinary matter is tightly coupled to radiation for a long period. Photons scatter from free electrons, electrons interact with atomic nuclei, and the combined plasma behaves differently from matter that can simply collapse under its own gravity. Pressure in the radiation resists compression, so ordinary matter cannot immediately fall into every small overdensity. Dark matter behaves differently. It does not participate in the same electromagnetic interactions, and once the conditions are appropriate, it can begin responding to the primordial gravitational pattern without being held up by radiation pressure in the same way. This distinction becomes one of the central stages in turning inflationary fluctuations into the later cosmic web. Small dark matter overdensities grow gradually, creating gravitational wells that deepen over time. The process is not an explosion of structure, it is long amplification. A region only slightly denser than average attracts additional matter, which increases its density, which strengthens its gravitational pull. Meanwhile, regions that begin slightly underdense tend to lose matter to their denser neighbours and become increasingly empty. The original pattern therefore sharpens. What began as tiny statistical differences develops into a contrast between concentrations and voids. The expansion of the universe continues throughout this process, so structure formation is always a competition between cosmic expansion and gravitational attraction. On sufficiently large scales, matter follows the general expansion. Within overdense regions, however, gravity can eventually become strong enough to slow the local expansion, halt it, and reverse it into collapse. Dark matter then forms bound structures called halos. These halos are not visible directly because dark matter does not emit light in the ordinary way, but they provide the gravitational framework into which ordinary gas can later fall. Their formation gives the universe a hidden architecture before most of its luminous structure appears. This architecture is hierarchical in the standard cosmological picture. Smaller gravitationally bound structures tend to form first and later merge into larger ones. The exact sequence depends on the nature of dark matter and on the primordial power spectrum, but the broad pattern is one in which modest, early concentrations assemble into progressively larger systems. Gas follows these growing wells, although its behavior is more complicated because it can heat, cool, radiate energy, form molecules, and eventually fragment. Once enough gas gathers in a halo and can lose sufficient thermal energy, portions of it become dense enough for stars to form. The first stars alter their surroundings through radiation, stellar winds, and later explosions. They produce heavier elements, reshape nearby gas, and create new conditions for subsequent generations of stars. Galaxies emerge as repeated cycles of collapse, cooling star formation, feedback, merging. And accretion unfold inside dark matter halos. The connection to inflation remains present throughout this much later history, but it is easy to lose sight of because so many additional processes intervene. Inflation does not specify the shape of an individual galaxy. It does not decide where a particular star forms or how a given galaxy merger unfolds. Instead, it supplies the statistical initial conditions from which gravity and later astrophysics operate. The large-scale distribution of matter remembers those initial conditions far more clearly than any single object does. Across immense volumes, galaxies are not arranged randomly. They form clusters, filaments, walls, and vast underdense regions known as voids. Together, these structures make up the cosmic web. Its form arises because gravitational collapse acts differently, depending on the geometry of the initial perturbations. Matter may collapse first along one direction to form sheet-like structures, then along another to create filaments, and finally gather into dense nodes where clusters of galaxies develop. Voids expand relative to their surroundings as matter drains away from them. The result is a network whose overall organization reflects the original distribution of primordial density variations. Numerical simulations make this connection especially vivid. When cosmologists begin with a nearly uniform distribution of dark matter containing tiny fluctuations with the statistical properties inferred from the early universe, then allow gravity to evolve the system through cosmic time, web-like structure naturally develops. The simulations do not need to place galaxies by hand along predetermined filaments. The pattern emerges from gravitational growth. Adding gas physics, star formation, black hole feedback, and other processes makes the calculation more complex, but the underlying skeleton still comes from the initial density field. This is one of the strongest conceptual links between inflationary cosmology and the visible universe. A fluctuation stretched beyond the Hubble scale during inflation can later return inside the horizon, influence the local distribution of matter, participate in the growth of a dark matter halo, and eventually contribute to the environment in which galaxies appear. The journey from quantum fluctuation to galaxy is therefore not a single transformation. It is a chain of changing physical regimes. Quantum field behavior becomes a primordial curvature perturbation. The perturbation becomes a density contrast. The density contrast grows under gravity. Dark matter collapses into halos. Gas falls into those halos and cools. Stars ignite. Galaxies assemble. Large structures merge and reorganize while the cosmic web continues to evolve. Each stage uses different physics, yet the initial pattern remains statistically connected to the earliest one. The cosmic microwave background provides a view of that pattern before most nonlinear structure formation has occurred. Its temperature and isotropies show the universe when the density variations are still small enough to be described with relatively simple perturbation theory. Galaxy surveys observe the same broad history at much later times after gravity has amplified the initial irregularities into a far more complex distribution. Comparing these different epochs gives cosmologists a way to test whether the same primordial spectrum can account for both early and late structure. The consistency is important because inflation does not merely need to produce fluctuations of roughly the right size, it has to produce the right distribution across scales. Too much primordial power on certain scales would generate excessive structure. Too little would delay or suppress the formation of galaxies and clusters. Strong departures from the observed statistical pattern would leave recognizable differences in both the microwave background and the later matter distribution. The amplitude of the primordial perturbations is therefore one of the most consequential numbers in cosmology, even though the underlying variations are small. A universe with much larger primordial fluctuations would become clumpy far earlier. A universe with much smaller ones could remain comparatively smooth for much longer. The observed cosmos occupies a regime in which structure formation proceeds gradually enough for complex hierarchy to develop over billions of years. This does not mean inflation uniquely predicts the exact universe without additional parameters. The amplitude and detailed scale dependence depend on the inflationary model, but the mechanism gives a natural reason for why nearly scale-invariant small perturbation should exist at all. Gravity then provides the amplifier. Dark matter provides much of the early scaffolding. Gas physics turns that scaffolding luminous. The cosmic web is the final large-scale expression of a pattern whose beginnings are almost unimaginably faint. By the time mature galaxies fill filaments and clusters, the quantum origin of the pattern is hidden beneath layers of nonlinear evolution, mergers, star formation, and feedback. Yet the connection can still be reconstructed statistically. The locations of individual galaxies are complicated outcomes, but the collective distribution preserves information about the primordial field. In this way, cosmic structure becomes one of inflation's longest consequences. Accelerated expansion may have lasted only a brief interval, but the perturbations associated with it continue evolving throughout nearly the entire subsequent history of the universe. Their growth also makes clear why inflation cannot continue forever in the region that becomes observable. Structure requires a later phase in which the inflationary expansion ends. The universe becomes filled with ordinary particles and radiation, and gravitational growth can begin under a very different expansion history. The seeds alone are not enough. The background must change. Inflation must release the universe into the hot state, in which those seeds can eventually become matter halos, stars and galaxies. That transition begins with the end of inflation itself, when the field driving accelerated expansion can no longer remain in the regime that sustained it. Inflation cannot remain the dominant state forever in the region that develops into the observable universe, because the later cosmos requires a radically different environment. Accelerated expansion has to stop the energy driving, it has to change form, and the universe has to enter a phase in which particles and radiation can fill space without being immediately diluted away. In the simplest slow-roll models, this transition begins when the inflaton field reaches a part of its potential where the conditions that sustained slow evolution no longer hold. The field may encounter a steeper slope, its kinetic energy may become more important, or the potential energy may fall enough that the effective negative pressure can no longer maintain accelerated expansion. The scale factor does not suddenly stop growing. Expansion continues, but the special inflationary acceleration ends. This distinction is essential because the universe after inflation is still an expanding universe. What changes is the dominant form of energy and the way that energy influences the expansion rate. During slow-roll potential, energy remains nearly constant while the field changes gradually. Near the end, that balance begins to fail. The field accelerates through its potential kinetic energy rises relative to potential energy, and the equation of state moves away from the inflationary regime. The mathematical condition for accelerated expansion is no longer satisfied. In many single-field models, this moment can be identified when the slow-roll parameters, which had remained much smaller than unity, grow to values indicating that the approximation has broken down. The precise threshold depends on how the model is described, but the physical meaning is straightforward. The field is no longer moving gently enough for its potential energy to dominate in the same way. Inflation loses the mechanism that had kept it going. This ending is often called the exit from inflation, and a viable model must provide one. Early versions of inflation made the importance of this requirement especially clear. A model could produce accelerated expansion successfully and still fail if it could not end in a way that left behind a sufficiently uniform hot universe. The difficulty was not merely stopping the expansion. It was stopping the inflationary state without destroying the very conditions inflation had been introduced to explain. Later models developed smoother mechanisms in which the field naturally evolves out of the slow-roll regime, allowing inflation to end throughout the relevant region, without leaving the universe excessively empty or irregular. In these scenarios, the end of inflation is not an arbitrary switch inserted by hand. It follows from the shape of the potential and the dynamics of the field. Once the inflaton reaches a steeper region, it can begin moving much more rapidly toward a lower energy state, in a simple potential with a minimum. The field may overshoot that minimum and oscillate around it. These oscillations are important because they mark a new dynamical regime. The field that had behaved almost like a constant vacuum energy now behaves more like a changing reservoir whose energy can be redistributed. The expansion rate responds accordingly. Accelerated expansion weakens, and the universe begins moving toward the hot particle-filled phase that follows. Not every inflationary model ends through this exact pattern. In hybrid inflation, for example, the termination can involve an additional field that becomes unstable once the inflaton reaches a particular value, causing inflation to end through a rapid transition. Other models use different interactions, modified gravitational dynamics, or several fields moving through a more complicated energy landscape. What they share is the requirement that the inflationary state must become unstable or dynamically inaccessible in the region that later becomes observable. There has to be a path from a state dominated by inflationary energy to one dominated by the ingredients of the hot Big Bang. The exit is therefore not a secondary detail. It is part of the central consistency test of the theory. A model that inflates but cannot end appropriately cannot describe the observed universe. The timing of the exit also matters. If inflation ends too early, the universe may not accumulate enough E-folds to solve the horizon and flatness problems or sufficiently dilute unwanted relics. If it continues much longer, that is not necessarily a problem for the observable patch, but it can alter which parts of the inflationary potential correspond to the scales measured in the cosmic microwave background. The predictions for primordial fluctuations depend on what the field was doing when those observable scales were stretched beyond the relevant horizon, and that timing is usually described by how many folds remained before inflation ended. The exit therefore acts as a reference point for connecting theory with observation. The shape of the potential near the end can influence not only when inflation stops, but also how the subsequent universe evolves. Once slow roll fails, the field can change rapidly enough that the simple approximations used during inflation are no longer reliable. The system can become highly dynamical. Oscillations, interactions with other fields, and the production of particles can all become important. The energy that had been stored primarily in the coherent inflaton background cannot simply vanish. For the hot Big Bang phase to emerge, that energy has to be transferred into other degrees of freedom. This transfer is the beginning of the process later described broadly as reheating. The end of inflation and reheating are therefore closely linked but not identical. Inflation ends when accelerated expansion ceases. Reheating concerns what happens to the inflationary energy afterward and how the universe becomes populated with ordinary particles and radiation. Depending on the model, the boundary between these stages can be gradual rather than sharp. Particle production may begin almost immediately as the inflaton starts oscillating, or the transfer may proceed through several intermediate stages. Some models allow a particularly rapid process known as preheating, in which coherent oscillations of the inflaton can produce other fields very efficiently through resonant effects. Other scenarios involve slower perturbative decay. The details remain uncertain because they depend on couplings between the inflationary sector and the particle physics that follows. The end of inflation also changes the fate of scales that have been stretched outward during accelerated expansion. During inflation, the characteristic Hubble scale behaves in a way that allows physical wavelengths to become larger than it. Once the expansion enters a decelerating regime, the relationship reverses. The horizon grows relative to those wavelengths, and modes that had effectively left during inflation can later return inside. Their preserved primordial perturbations then become available to influence radiation and matter. In this sense, ending inflation is necessary not only to create a hot universe, but also to allow the fluctuations generated during inflation to re-enter causal evolution at later times. The same transition that releases the universe from accelerated expansion prepares the conditions in which its primordial pattern can eventually become visible. Yet the precise moment when inflation ends is not something observations have directly witnessed. It is inferred through models and through the consistency of their predictions with later data. Different potentials can produce similar observable spectra while ending in different ways. This creates a region of uncertainty between the well-tested hot Big Bang history and the earlier inflationary phase. The The broad requirement is clear accelerated expansion must cease, and its energy must be converted. The detailed route remains model-dependent. That uncertainty is especially important because the thermal state produced afterward affects the interpretation of inflation itself. The duration and efficiency of the transition influence the mapping between present cosmological scales and the points on the inflationary potential from which their perturbations originated. Reheating is therefore not merely an afterthought placed between inflation and conventional cosmology. It feeds back into how inflationary predictions are calculated. The end of inflation is best seen as a threshold rather than a final event. On one side lies a universe dominated by a slowly evolving source of nearly constant energy, expanding at an accelerated rate and stretching quantum fluctuations to cosmic scales. On the other lies a universe in which that source is changing rapidly, its energy becoming available for particle production, while expansion continues under a different set of conditions. The elegant simplicity of slow roll gives way to a more complicated physical transition. The geometry has already been transformed. The primordial fluctuations have already been laid down. What remains is to fill the enlarged universe with heat. That conversion is the bridge into the familiar hot Big Bang, and understanding it requires following the inflationary energy as it leaves the field that drove expansion and becomes the particles and radiation of the young cosmos. Reheating is the stage in which the energy that once sustained inflation is transformed into the particles and radiation required for the hot Big Bang universe. The name can be slightly misleading because it sounds as though the universe had previously been hot-cooled and then simply warmed again in an ordinary thermal sense. In many inflationary scenarios, the important point is different. During inflation, the energy density is dominated by the field or mechanism driving accelerated expansion, while any pre-existing particles and radiation are rapidly diluted. By the time inflation ends, the universe can be extremely empty of ordinary matter, even though the inflationary energy itself remains enormous. Reheating describes the conversion of that stored energy into a dense population of particles which can interact, scatter, and eventually approach a thermal state. The hot universe familiar from standard Big Bang cosmology is therefore not necessarily the state inflation begins with. It is the state inflation must somehow create when it ends. In the simplest single-field picture, the inflaton reaches the lower part of its potential after slow roll fails and begins oscillating around a minimum. Those oscillations can contain energy. If the inflaton is coupled to other quantum fields, it can transfer energy into them. The produced excitations may correspond to particles or to highly occupied field modes that later behave like particles as the system evolves. The details depend on the couplings, masses, and structure of the underlying theory. There is no single reheating mechanism known to be the one nature used. What all viable scenarios require is a sufficiently effective transfer from the inflationary sector into the degrees of freedom that populate the later universe. In one broad class of models, this transfer proceeds through decays. The inflaton oscillates and gradually loses energy by producing other particles, rather as an unstable particle can decay into lighter states. If those products interact efficiently enough, they scatter among themselves and move toward thermal equilibrium. A characteristic reheating temperature can then be assigned to the resulting plasma, although the concept of a single temperature becomes fully meaningful only after the system has become sufficiently close to thermal equilibrium. Before that point, the universe can contain abundant particles while still being far from a simple thermal distribution. Reheating is therefore not necessarily instantaneous, and the word does not refer to one sharply defined moment. It can describe an extended transition from coherent field energy to a thermal bath. In some models, the process can be much more violent than slow perturbative decay suggests. When the inflaton oscillates coherently, its interaction with other fields can trigger resonant amplification, causing certain modes to grow extremely rapidly. This stage is often called preheating. Large amounts of energy can move out of the inflaton condensate in a comparatively short interval. The produced fields may initially occupy a highly non-thermal state, after which nonlinear interactions and scattering redistribute the energy. Thermalization can follow later. Preheating is not required in every model, and its efficiency can vary widely, but it illustrates how complicated the end of inflation may become once the simple slow-roll regime is left behind. The universe can pass from an almost homogeneous inflationary field to a highly dynamical network of interacting quantum fields before settling into the smoother thermal description used in conventional early universe cosmology. This transition matters because the hot Big Bang model begins from a universe filled with energetic particles and radiation. Once that state has been established, the subsequent thermal history becomes much better constrained. As expansion continues, the plasma cools. Particle species appear or disappear from equilibrium according to their interactions and masses. Matter and antimatter can annihilate. At lower temperatures, protons and neutrons participate in primordial nucleosynthesis, producing much of the early helium and small amounts of other light nuclei. Much later, electrons combine with nuclei to form neutral atoms, allowing the cosmic microwave background to travel freely. Inflation does not replace these processes. Reheating places the universe into the conditions from which they can occur. This is why inflation and the hot Big Bang are better regarded as neighboring parts of one possible cosmological history rather than competing explanations. Inflation addresses questions about the initial conditions of the hot phase and the origin of primordial perturbations. The hot Big Bang describes the thermal evolution that follows. Reheating is the bridge between them. The properties of that bridge remain uncertain, and the uncertainty has consequences. The duration of reheating affects how the scale factor grows between the end of inflation and the onset of radiation domination. The effective equation of state during this interval can vary depending on how the inflaton oscillates and how energy is transferred. These differences alter the relationship between scales observed today and the moments during inflation when their primordial fluctuations were generated. A given feature in the cosmic microwave background may correspond to one point on an inflationary potential if reheating is rapid, and another point if reheating lasts longer. Predictions for quantities such as the spectral tilt and the strength of primordial gravitational waves can therefore depend sometimes subtly and sometimes significantly on assumptions about reheating. The post-inflationary thermal history reaches backward into the interpretation of inflation itself. Reheating also has to be hot enough for the later universe to develop as observed, but not every possible temperature is equally harmless. If the maximum temperature is very high, particles or relics associated with speculative high energy, theories could potentially be regenerated after inflation had diluted their earlier population. This connects reheating back to the relic problem. Inflation can remove unwanted monopoles or other heavy remnants only if the later thermal history does not simply produce them again in unacceptable numbers. The allowed reheating temperature can therefore depend on particle physics beyond the standard model. Conversely, some important processes may require sufficiently high temperatures. Proposed mechanisms for creating the observed imbalance between matter and antimatter can depend on the thermal environment or on non-thermal processes occurring during reheating. Dark matter production may also be sensitive to the maximum temperature reached, and to which particles are generated directly from the inflaton. Reheating is therefore a crossroads where inflationary cosmology meets particle physics. Its details can influence not only the expansion history but also the composition of the later universe. Yet these details are difficult to observe directly. No light survives from reheating in the ordinary sense because the universe remains opaque for a long time afterward, and the processes occur far earlier than the formation of the cosmic microwave background. Information must instead be inferred through indirect consequences. The primordial perturbation spectrum carries some dependence on the expansion history between inflation and radiation domination. A stochastic background of gravitational waves, if present across suitable frequencies, could in principle retain information about the equation of state during poorly observed early epochs. Relic abundances might also constrain how hot the universe became. None of these routes has yet reconstructed reheating uniquely. The stage remains one of the less directly tested pieces of the inflationary narrative. Even the maximum temperature and the point at which a stable radiation-dominated era begins are model-dependent. This uncertainty does not erase the broad requirement. Something has to convert inflationary energy into ordinary degrees of freedom. Without that conversion, the universe emerging from inflation would remain dominated by the wrong form of energy and would not enter the thermal sequence that successfully explains later observations. Reheating is therefore simultaneously necessary and incompletely understood. It is one of the places where the smooth conceptual outline of inflation becomes dependent on detailed microphysics. The inflationary expansion can be described using a small set of background quantities. Reheating may involve decays, resonances, rescattering thermalization and interactions among fields whose identities are not yet known. That complexity is not an optional decoration around the theory. It determines how the universe moves from the inflationary state to the first well-established stages of hot cosmology. Once the energy is distributed into a hot plasma and radiation becomes dominant, the later universe begins following the familiar thermal path. The primordial perturbations created during inflation remain embedded within that plasma as small variations in density and curvature. They survive the transition and continue evolving until much later they leave their imprint on the cosmic microwave background. Reheating itself is hidden, but the patterns that pass through it are not completely erased. The next observable window therefore appears long after the inflationary engine has disappeared and long after the universe has thermalized. It appears in ancient radiation released when neutral atoms first allow light to travel freely, carrying within tiny temperature differences a statistical record of fluctuations generated at a far earlier time. The cosmic microwave background does not show reheating directly, but it provides one of the clearest surviving tests of the inflationary conditions that came before it. The cosmic microwave background is separated from inflation by an immense stretch of early cosmic history, yet it remains one of the clearest places to look for inflation's fingerprints. The radiation itself was released when the universe had cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that transition, free electrons scattered photons so efficiently that light could not travel far without being redirected. Once neutral atoms formed, the scattering rate dropped sharply, and photons began moving through space much more freely. Those photons have been travelling ever since, stretched by cosmic expansion into the faint microwave glow observed across the sky today. The radiation, therefore, does not come directly from the inflationary epoch. It comes from a much later moment when the universe was already hundreds of thousands of years old. What makes it useful is that the matter and radiation present at that time were carrying forward the primordial perturbations established much earlier. Tiny differences in density and gravitational potential affected the temperature of the photons, and those differences became preserved as a subtle pattern across the microwave sky. The cosmic microwave background is therefore not a photograph of inflation, but it is a record shaped by inflationary initial conditions. Its nearly uniform average temperature reflects the broad smoothness of the early universe, while its small anisotropies, the slight differences from one direction to another, reveal the primordial irregularities that later grow into structure. The pattern is extraordinarily weak compared with the average temperature, yet its statistical organization contains far more information than a simple measure of smoothness. Cosmologists do not only ask how large the temperature variations are, they examine how those variations are distributed across angular scales, how strongly one region is correlated with another, how the polarization of the radiation is arranged, and whether the resulting spectrum matches the predictions of particular early universe models. This is where inflation becomes observationally vulnerable. A successful model must generate perturbations whose statistical properties agree with what the microwave background actually contains. One of the central quantities is the primordial scalar power spectrum, which describes how the strength of curvature perturbations depends on scale. Many simple inflationary models predict a spectrum that is nearly scale invariant. In broad terms, this means that the primordial fluctuations do not strongly prefer one particular scale over another. The phrase nearly matters. Perfect scale invariance would correspond to a particular idealized spectral shape, but observations indicate a small departure from that limit. The scalar spectral index commonly used to describe the tilt is slightly below the value associated with exact scale invariance. In physical terms, the amplitude of primordial fluctuations changes gently with scale, rather than remaining perfectly constant in the scale invariant sense. That small tilt is not an inconvenience added to the theory after the fact. In many slow-roll models, it arises naturally because the inflationary expansion rate and the motion of the field are changing gradually while different wavelengths are being stretched. Modes associated with different scales leave the relevant inflationary horizon at slightly different times when the background conditions are not quite identical. The resulting spectrum therefore contains a faint record of the evolution of the inflationary state. Measurements of the cosmic microwave background have shown that the scalar spectral index is close to, but measurably different from exact scale invariance. This result is highly important because a completely featureless primordial spectrum is not what is observed. The data instead favor a gentle red tilt, meaning that power changes slightly toward larger and smaller scales in the manner captured by a spectral index below unity. Many inflationary models can produce such a tilt, but not all models produce the same value. As measurements have become more precise, some potentials and parameter ranges have become less compatible with the data, while others remain viable. The microwave background therefore does not merely support the broad idea that primordial perturbations existed. It helps discriminate among possible mechanisms for producing them. Another important test comes from the shape of the temperature power spectrum itself. The microwave background contains a sequence of acoustic peaks produced by sound waves in the early photon and baryon plasma. These peaks arise long after inflation, but their overall pattern depends on the primordial perturbation supplied to that plasma. Inflationary models typically generate perturbations with the phase, relationships needed to produce a highly coherent acoustic pattern. The observed peaks are therefore consistent with a universe whose initial perturbations were laid down in a simple correlated way at very early times. The peaks also allow precise measurements of later cosmological quantities, including the matter, content, baryon density, expansion history, and spatial geometry. Those later parameters must be understood well because they affect how the primordial signal is projected onto the sky. Testing inflation is never simply a matter of reading one number from one image. It requires separating the physics of the primordial spectrum from the transfer processes that modify the radiation before it reaches observation. Polarization adds another layer. Thomson scattering the interaction between photons and free electrons can generate linear polarization when the incoming radiation field has the appropriate directional asymmetry. This produces characteristic polarization patterns across the microwave sky. One component, commonly called E-mode polarization, has been measured with high precision and is consistent with the same broad cosmological framework that explains the temperature fluctuations. The correlations between temperature and polarization give additional information about the primordial perturbations and the later ionization history of the universe. Another component called B-mode polarization is especially interesting because primordial gravitational waves generated during inflation could produce a distinctive large-scale B-mode pattern. That possibility provides a separate test and leads toward one of the most sought-after signatures in inflationary cosmology. The temperature and E-mode data already impose strong limits on inflationary models, even without a primordial B-mode detection. They constrain the scalar spectral index, the amplitude of fluctuations, possible departures from Gaussian statistics, and other features that different models predict differently. Simplicity is important here. Many of the most economical inflationary scenarios predict perturbations that are nearly Gaussian and close to adiabatic, meaning that different components of the cosmic fluid begin with density variations that are related in a common way rather than fluctuating independently. Observations are broadly consistent with these properties. Strong primordial non-Gaussianity has not emerged in the forms that would decisively overturn the simplest single-field, slow-roll picture. Likewise, large isocurvature contributions which would indicate additional independent modes in the primordial composition are tightly constrained. These absences matter because inflation is tested not only through what appears in the data, but also through what does not. A model that predicts strong signatures where the sky remains quiet can be ruled out or forced into a narrow parameter range. Yet the success of these broad predictions should not be turned into a claim that the cosmic microwave background proves inflation uniquely. Other early universe mechanisms can be constructed to generate some similar features, and inflation itself is a family of models rather than one fixed theory. The observational situation is therefore one of strong consistency rather than direct identification. The microwave background possesses several properties naturally expected from inflation: large-scale uniformity, a nearly scale invariant spectrum of primordial perturbations, slight spectral tilt, approximate Gaussianity, and coherent acoustic structure. Together, these features make inflation an exceptionally successful framework for organizing early universe data. But they do not reveal the inflaton directly specify a unique potential, or show exactly how inflation began and ended. The strength of the evidence lies in the pattern as a whole. A proposal for the early universe must account simultaneously for the smooth background and the small fluctuations, for their scale dependence and their correlations, and for the later evolution that converts those primordial conditions into the observed acoustic peaks. Inflation achieves this with remarkable economy across many models, while increasingly precise observations continue to narrow which versions remain plausible. The cosmic microwave background therefore acts less like a single fingerprint than like a detailed statistical archive. It preserves enough information to test the early universe, but the archive has to be interpreted through a chain of physical processes extending from inflation to reheating, radiation, domination, plasma oscillations, recombination, and the later expansion of space. Every stage modifies the signal without erasing its primordial origin. What survives is subtle but structured. The temperature variations reveal the scalar perturbations from which matter structure grows, while polarization opens a possible path toward an even more direct probe of inflationary dynamics. That second path depends on tensor perturbations, fluctuations of space-time itself. If inflation generated them strongly enough, their imprint may still be hidden in the polarization of the microwave background, waiting beneath foreground emission, gravitational lensing, and instrumental limits. The scalar evidence is already precise. The tensor signature remains the missing prize. Primordial gravitational waves occupy a special place in inflationary cosmology because they would arise not from collapsing stars or merging black holes, but from quantum fluctuations in space-time during the inflationary era itself. In general relativity, gravity is expressed through the geometry of space-time, and that geometry can support wave-like disturbances. During inflation, quantum fluctuations do not affect only scalar fields. The gravitational field can fluctuate as well. If those tensor fluctuations are stretched to cosmic scales by accelerated expansion, they can survive as a primordial background of gravitational waves. Their existence would connect the quantum behavior of space-time to an era far earlier than any directly observed astrophysical source. In that sense, they would provide a particularly distinctive window into inflation, because the amplitude of the tensor signal depends on the energy scale and dynamics of the inflationary expansion. A stronger inflationary energy scale generally allows larger tensor fluctuations in many simple models, while lower scale or flatter plateau models can produce signals that are much smaller. The quantity commonly used to compare these tensor fluctuations with the scalar perturbations responsible for density structure is the tensor to scalar ratio. It measures the relative strength of the primordial tensor spectrum compared with the scalar spectrum. A large value would mean that inflation produced a comparatively strong gravitational wave background. A small value would mean that scalar perturbations dominate much more strongly. The ratio is therefore not merely a descriptive statistic. It can eliminate models whose predicted tensor amplitude is too large. The difficulty is that primordial gravitational waves cannot be detected in the same way as the gravitational waves produced by modern compact objects. Their characteristic wavelengths have been stretched enormously, and the most accessible proposed signature lies in the polarization of the cosmic microwave background. Polarization patterns on the sky can be decomposed into different geometric components. One is called E-mode polarization, another is called B-mode polarization. Scalar density perturbations generate E-modes efficiently at first order, while primordial tensor perturbations can generate a distinctive large-scale B-mode pattern. This makes B-mode polarization an attractive target because it can separate a tensor contribution from the much stronger scalar signal in a way that temperature measurements alone cannot. The idea sounds clean in principle, but the actual sky is considerably more complicated. Dust within the Milky Way emits polarized radiation. Synchrotron emission from charged particles moving through galactic magnetic fields can also be polarized. These foregrounds can imitate or obscure the patterns being sought. In addition, gravitational lensing by large-scale structure bends the paths of cosmic microwave background photons and converts some E-mode polarization into B-modes. Lensing therefore creates a secondary B-mode signal, even if primordial gravitational waves are extremely weak. Instruments must distinguish the inflationary component from galactic foregrounds, lensing instrumental noise and systematic effects. This is one reason the search has advanced through tighter limits rather than through a secure primordial detection. The BICEP and Keck program has been central to this effort by observing microwave polarization from regions of the sky selected for relatively low foreground contamination and combining those measurements with data at other frequencies. An analysis using observations through 2018 together with information from Planck and WMAP, found no convincing primordial B-mode signal and constrained the tensor to scalar ratio to be less than about 0.036 at 95% confidence at the reference scale used in that analysis. The number is important not because it closes the search, but because it sharply reduces the space available to inflationary models that predict strong tensor production. Models in which the inflaton moves across certain steep or simple potentials can generate tensor signals larger than the observational limit and are therefore strongly disfavored in their simplest forms. Models predicting much smaller tensor amplitudes remain viable. The absence of a detection does not mean inflation has failed. Inflation is a broad class of mechanisms, and many versions predict primordial gravitational waves too weak for present experiments to see. This distinction is essential. A future detection of a primordial tensor signal with the appropriate properties would provide powerful new evidence about the inflationary epoch. Continued non-detection instead acts mainly as a filter, progressively excluding models that require a signal above improving experimental limits. The scientific value therefore grows in either direction. A detection would reveal new physics. A stronger upper bound would narrow the possible inflationary energy scales and potentials. The tensor signal also carries a deeper theoretical attraction because it may be tied more directly to the expansion rate during inflation than many scalar observables are. Scalar perturbations depend both on the expansion rate and on how the inflation-driving degrees of freedom evolve. Tensor perturbations arise from fluctuations in spacetime itself, making their amplitude especially informative about the background inflationary geometry. In simple, slow-roll models, measuring both the scalar spectrum and a tensor signal could constrain the shape of the inflationary potential far more tightly than scalar measurements alone. It could also provide clues about how far the inflaton moved through its potential during the observable part of inflation. The lack of such a signal leaves substantial degeneracy among models. Several very different inflationary mechanisms can produce similar scalar spectra, while predicting tensor amplitudes ranging from potentially detectable to effectively negligible. This is one reason the search for B modes remains so important, even after the scalar sector has been measured with great precision. The scalar perturbations show that the early universe contained the right kind of initial structure for galaxies and the cosmic microwave background. Tensor perturbations would probe an additional part of the inflationary dynamics that has not yet been observed. There is also a distinction between primordial B modes and B modes already measured from gravitational lensing. Lensing B modes are real and scientifically useful, but they are generated much later as matter structures distort the path of microwave background radiation. They do not constitute a detection of primordial gravitational waves. Removing or reducing this lensing contribution, a process called delensing, is therefore an important part of future searches. Better measurements at multiple frequencies are also needed to model galactic foregrounds. The challenge is not simply sensitivity, it is separation. A primordial signal may be faint enough that every competing source has to be understood with comparable precision. The search therefore becomes a test of both cosmology and experimental control. If a primordial B-mode pattern is eventually isolated, its scale dependence and statistical properties will matter as much as its mere presence. A signal consistent with inflation would need to fit the expected cosmological correlations and resist explanations from foregrounds or later astrophysical processes. If no signal appears as sensitivity improves, some inflationary models will continue to disappear from consideration, while others survive with smaller tensor predictions. The process illustrates a broader strength of inflation as a scientific framework. Inflation is flexible enough to contain many models, but it is not infinitely flexible once detailed observations are imposed. The cosmic microwave background constrains the scalar spectral tilt, the amplitude of perturbations, non-Gaussianity, isocurvature modes and tensor strength. Each additional measurement cuts across the model space from a different direction. Primordial gravitational waves are especially valuable because they could distinguish models that otherwise look almost identical in the scalar data. This makes their absence informative rather than empty. The missing tensor fingerprint is a boundary drawn around the theory. It says that if inflation occurred, the version realized by nature cannot produce a primordial tensor background stronger than the observational limits allow. That boundary has already placed pressure on several simple high tensor scenarios, once considered natural starting points. At the same time, it leaves a large landscape of lower tensor models untouched. The search therefore does not approach a simple yes or no verdict. It gradually changes which inflationary stories remain plausible. This is the point at which the phrase cosmic inflation begins to lose its appearance of describing one theory. The same broad mechanism can solve the horizon problem, flatten space, dilute relics, and generate primordial perturbations, yet different implementations predict different tensor amplitudes and different observable details. The continuing silence in primordial B modes therefore leads directly to the next question. Not whether inflation has one prediction, but how many distinct versions of inflation remain compatible with the universe that has actually been measured. The word inflation can make the early universe sound as though cosmology is describing one theory with one field, one potential, and one fixed set of predictions. In reality, inflation is a broad class of models united by a common dynamical idea. For some interval, the expansion of the universe accelerates strongly enough to alter causal structure, suppress curvature, dilute relics, and stretch microscopic fluctuations to cosmological scales. Once that shared framework is accepted, many different physical implementations become possible. Some use a single scalar field evolving through a smooth potential. Others involve several fields whose interactions shape the background and the perturbations together. Some rely on broad plateau-shaped potentials, some on steeper forms, some on phase transitions, and some on mechanisms in which the effective inflationary degree of freedom emerges from more complicated gravitational or particle physics. The success of inflation as a framework therefore does not mean that cosmology has already identified the specific theory realized by nature. It means that a large family of theories has been forced to compete against the same increasingly precise observations. The simpler starting point is single-field slow-roll inflation. In these models, one effective scalar field dominates the dynamics, while its potential energy drives accelerated expansion. The field changes gradually, inflation lasts long enough to generate the required growth, and quantum fluctuations in that field become the main source of scalar perturbations. This setup is attractive because it is mathematically economical and often produces a set of broad properties that resemble what is observed nearly scale, invariant primordial fluctuations, approximate Gaussian statistics, predominantly adiabatic perturbations, and a calculable relationship between the shape of the potential and quantities measured in the cosmic microwave background. But even within this apparently narrow category, there are many distinct models. A potential can be relatively steep, gently curved, asymptotically flat, or marked by features. Each choice changes how quickly the field evolves and how the inflationary expansion rate changes while observable scales are being generated. Those differences feed into the scalar spectral tilt and the tensor, to scalar ratio 2 of the most useful observational quantities for comparing models. The scalar spectral tilt describes how the strength of primordial curvature perturbations changes with scale. The tensor to scalar ratio describes how strong primordial gravitational waves are relative to scalar perturbations. Two models can both solve the horizon and flatness problems, yet predict different values for these quantities. This is where observation begins separating the family. Models that produce too much tensor power can come under pressure even if their scalar predictions look acceptable. Models that produce a spectral tilt inconsistent with the microwave background can be disfavored for a different reason. The theory is therefore tested not by asking only whether inflation occurred, but by asking whether a particular implementation lands in the small region of observable parameter space that the universe permits. This has changed the status of several historically simple potentials, forms that once served as natural textbook examples, because of their mathematical simplicity, can predict a tensor signal larger than observational limits allow in their most basic versions. Their role in teaching remains useful because they clearly illustrate the mechanics of slow roll, but their status as realistic descriptions of nature becomes weaker as data improve. By contrast, Many plateau-like or otherwise gently flattening potentials can generate a red-tilted scalar spectrum while keeping tensor production comparatively small. In a range of simple, single-field, slow-roll settings, such models fit microwave background constraints more comfortably. This does not prove that the true inflationary potential has a plateau. It shows how observation reshapes theoretical preference. A model can remain elegant while becoming observationally strained, and another can become more attractive because its predictions fall naturally inside the measured region. Multi-field inflation expands the possibilities further. If more than one field participates, the path through the underlying energy landscape can curve interactions between fields, can alter the perturbations and fluctuations can arise not only along the direction of the background motion, but also perpendicular to it. Those additional degrees of freedom can produce effects that simple single-field models suppress. Isocurvature perturbations can appear, meaning different components of the cosmic medium may initially fluctuate relative to one another rather than sharing a single common pattern. Non-Gaussianity can also become more prominent, revealing correlations that depart from the near-Gaussian statistics predicted by many simple models. The absence of strong evidence for these signatures does not rule out multi-field inflation, because multi-field models can be built to produce very small effects. But observational limits restrict how strongly additional fields could have influenced the visible perturbations. Hybrid inflation introduces another kind of structure. In a typical hybrid picture, one field can control the slow evolution, while a second field triggers the end of inflation after a critical condition is reached. Inflation therefore ends not simply because the original field rolls into a steep region, but because the configuration becomes unstable and a new transition begins. This illustrates how the graceful exit from inflation can be built into the model in more than one way. It also shows why reheating and the end of inflation cannot be completely separated from the theory that drives the earlier expansion. Different exit mechanisms can produce different post-inflationary histories, and those histories alter how observable scales are mapped back onto the inflationary potential. Other scenarios change the gravitational side of the picture rather than merely adding fields. A theory may contain higher curvature terms or other modifications that can be rewritten under appropriate conditions as an effective scalar degree of freedom. From the perspective of inflationary observations, such models can resemble ordinary scalar field inflation, even though their deeper interpretation is different. This creates an important form of degeneracy. Very different microscopic theories can lead to nearly the same predictions for the scalar tilt and tensor amplitude. Measurements can then exclude regions of theory space without identifying a unique underlying mechanism. The problem resembles hearing a small set of notes from behind a wall and trying to determine which instrument produced them. Better measurements reveal more of the pattern, but different sources can still sound unexpectedly similar. Non-Gaussianity is one way to add more notes. The simplest slow-roll models often predict primordial fluctuations that are extremely close to Gaussian. More complicated interactions, additional fields, or unusual kinetic structures can enhance departures from Gaussian statistics. Cosmologists therefore search for specific correlation patterns in the cosmic microwave background and large-scale structure. A convincing detection of a characteristic form of primordial non-Gaussianity could immediately reshape the inflationary landscape, favoring some mechanisms and strongly disfavoring others. So far, the absence of a large signal keeps the simplest possibilities viable while limiting models that require strong departures. Isocurvature searches play a similar role. If multiple independent components contributed significantly to the primordial perturbations, traces might remain in how different matter and radiation species were initially distributed. Tight limits on such contributions again favor simplicity in the observable sector, though they do not prove that only one field existed. This pattern repeats across inflationary cosmology. Observations usually constrain behavior more directly than they identify ontology. They can reveal that the primordial fluctuations are nearly adiabatic, nearly Gaussian, and slightly tilted, and that any tensor contribution must be small enough to respect observational limits. Those facts narrow the set of possible models. They do not yet reveal the name or particle identity of the field that generated them. Even the concept of a potential may be only an effective description of deeper physics. A model that looks like a simple scalar field at inflationary energies could emerge from a more complicated theory involving symmetries, extra fields, or modified gravity. The observable universe may preserve only a compressed record of that deeper structure. This is why inflation remains both powerful and unfinished. It is powerful because broad classes of models make quantitative predictions that can be tested. It is unfinished because several very different mechanisms still survive those tests. Better measurements continue to reduce the space. Stronger limits on primordial gravitational waves remove some high tensor scenarios. More precise measurements of the scalar spectrum constrain the allowed evolution of the inflationary background. Searches for running features, non-Gaussianity, and isocurvature perturbations probe additional dimensions of the model space. Large-scale structure surveys extend these tests beyond the microwave background. Each result makes the family smaller or forces models into more specific regimes. Yet no observation has selected one unique inflationary theory as the final description. The phrase cosmic inflation therefore names a successful organizing principle rather than a completed microscopic theory. Accelerated expansion may be the shared chapter, but the mechanism writing that chapter remains uncertain. That uncertainty leads naturally to the final question. After inflation has solved several classic problems, generated a pattern consistent with the microwave sky, survived stringent limits on tensor modes and remained compatible with large-scale structure, is there enough evidence to say that inflation truly happened, or only enough to say that it remains one of the strongest explanations available? Inflation now sits in an unusual position in cosmology. It is neither a vague speculation added to the beginning of the universe, nor a fully confirmed chapter whose physical details are known. It is a framework with substantial explanatory power, strong consistency with several important observations and unresolved questions at almost every level of its underlying mechanism. The distinction matters because the success of inflation is often summarized too simply. It can explain why the observable universe is so smooth across large scales, why spatial curvature is so small, why certain hypothetical relics could have been diluted, and how primordial fluctuations might have been generated with statistical properties close to those measured in the cosmic microwave background. These achievements make inflation one of the most influential ideas in modern cosmology. But an idea can be successful without being complete, and inflation remains incomplete in exactly the places where the earliest physics becomes hardest to test. The first uncertainty is the most basic one. No known observation has identified the physical field or mechanism that drove inflation. The inflaton is a useful theoretical name, not a discovered particle. A scalar field can reproduce the required behavior in many models, and the potential energy of such a field can sustain accelerated expansion, but nature has not revealed which field, if any, played that role. Several different constructions remain compatible with present cosmological data. Some use one field, some use several. Some arise from modified gravitational dynamics, and some emerge only as effective descriptions of deeper theories. The broad phenomenon can therefore remain plausible while its microscopic identity stays hidden. A second uncertainty concerns how inflation begins. The equations of a chosen model can describe an inflationary phase once appropriate conditions are supplied, but that is not the same as explaining why those conditions existed. Some models allow inflation to start from a fairly broad range of states. Others require the field to begin in a particular region of its potential, or with sufficiently small gradients and kinetic energy. The issue becomes especially difficult when the universe is traced toward earlier and more extreme conditions where classical gravity may no longer provide a complete description. Inflation can move the explanatory boundary backward by replacing some finely tuned hot Big Bang conditions with a dynamical process, but it does not automatically remove every question about initial conditions. It can explain why a region becomes smooth and flat after inflation starts, while leaving open why the region was suitable for inflation in the first place. This is one reason inflation should not be equated with the absolute beginning of the universe. The framework describes a possible early phase, not necessarily the first moment of existence. Whether anything preceded inflation, and whether the concept of before even remains meaningful in the relevant quantum gravitational regime is not known. Some proposals imagine an earlier contracting phase followed by a bounce. Others place inflation inside a larger quantum cosmological setting. Some models lead toward eternal inflation, where inflation ends in some regions, but continues elsewhere, potentially producing an enormous collection of regions with different histories. Eternal inflation is not a separate observation. It is a behavior that can arise in certain inflationary models when quantum fluctuations and background expansion interact in particular ways. Whether that regime actually occurs in nature and how its predictions should be defined and tested remains unsettled. These questions reach beyond the observational successes that first made inflation attractive. The uncertainty continues at the other end of the inflationary era. Reheating must convert the energy associated with inflation into particles and radiation, but the detailed mechanism is unknown. The inflaton, if it existed, would need to couple somehow to other fields. Those couplings would determine how quickly energy is transferred, what particles are produced, how high the temperature becomes, and how long the universe takes to settle into the radiation-dominated hot Big Bang phase. Different reheating histories change the connection between scales observed today and the part of inflation that generated them. The uncertainty is therefore not isolated after inflation. It feeds backward into predictions for inflation itself. A model can fit the cosmic microwave background under one assumed reheating history and shift slightly under another. Better knowledge of reheating would sharpen the interpretation of the earlier phase, but no direct observation has yet reconstructed that transition. The missing primordial gravitational wave signal adds another layer. Inflation can generate tensor perturbations, but their strength varies widely between models. Searches for the distinctive polarization pattern they could leave in the cosmic microwave background have not produced a secure primordial detection. This absence does not disprove inflation. It excludes or places pressure on models that predict a tensor signal larger than observational limits permit. Lower tensor models remain viable. The scientific situation is therefore asymmetric. A sufficiently clear primordial tensor detection with the expected cosmological properties would provide a powerful new line of evidence about the inflationary expansion. Continued non-detection instead narrows the family of possible models without eliminating the framework as a whole. The scalar perturbations already provide a stronger area of agreement. The primordial spectrum inferred from the cosmic microwave background is close to scale invariant but not exactly so approximately Gaussian, and largely adiabatic, all properties that arise naturally in many simple inflationary scenarios. These observations are among the strongest reasons inflation remains compelling, yet they do not identify inflation uniquely. Other early universe mechanisms can sometimes reproduce parts of the same observational pattern, though often with different theoretical costs or additional signatures. Scientific confidence therefore depends not on one prediction alone, but on how economically a framework accounts for the full collection of evidence. Inflation performs well by that standard, but the possibility of alternatives means that consistency should not be confused with direct proof. The deepest unresolved issue may lie where inflation meets quantum gravity. Inflation relies on quantum fluctuations while the background geometry is described gravitationally. This combination can be treated successfully using quantum field theory and curved spacetime across the regime relevant to many calculations. But if the history is pushed towards still earlier or higher energy conditions, a complete quantum theory of gravity may become necessary. No experimentally established theory currently provides that final description. Without it, questions about singularities, the origin of spacetime, the ultimate initial state, and the global behavior of inflation remain open. Inflation may be part of a deeper theory, or may eventually be replaced by a mechanism that reproduces its successful predictions in a different way. At present, the data do not force a unique answer. This uncertainty does not reduce cosmology to guesswork. It defines the boundary between what is measured, what is inferred, and what remains theoretical. The later hot Big Bang history is supported by a dense network of observations. The primordial perturbations are measured through the microwave background and large-scale structure. Their properties are consistent with broad inflationary expectations. The tensor sector remains constrained rather than detected. Reheating remains largely reconstructed through models. The identity and origin of the inflationary mechanism remain unknown. The earlier-than-inflation regime is more uncertain still. Each step backward therefore carries a different level of confidence, and keeping those levels separate is essential to a precise account of the early universe. Inflation is strongest when treated neither as certainty nor as a disposable idea. It is a framework that explains several otherwise puzzling features, with one coherent period of accelerated expansion, and that produces quantitative predictions capable of being tested. Some versions have already been weakened or excluded by observation. Others remain comfortably compatible with current data. Future measurements of microwave background polarization, large-scale structure, primordial statistics, and possible gravitational wave backgrounds may narrow the field further. They may reveal a distinctive signature that points toward a particular inflationary mechanism, or they may continue tightening the limits until the surviving models look very different from the simplest versions first studied. The final scientific judgment therefore remains measured. Inflation may indeed describe a real episode in the earliest accessible history of the universe. It explains too much and predicts too much to be dismissed casually. But the field that drove it has not been identified, its beginning has not been observed, its reheating process has not been reconstructed, and its primordial tensor signal has not been securely found. The theory remains powerful because it turns initial conditions into dynamics and microscopic fluctuations into cosmic structure. It remains unfinished because the mechanism beneath those successes is still hidden. At the edge of present knowledge, inflation is not a closed answer to the origin of the universe. It is a remarkably effective bridge between what can be observed and a deeper beginning that science has not yet reached. The story of cosmic inflation ends without a final boundary drawn around it. The observable universe carries a remarkable degree of order, from its near-flat geometry to the faint primordial pattern preserved in the cosmic microwave background, and inflation offers a coherent way to understand how many of those features could have emerged from one early period of accelerated expansion. A small causal region can become immense. Curvature can fade from observational importance. Ancient relics can become vanishingly rare. Quantum fluctuations can be stretched outward until gravity is able to turn them much later into the scaffolding of galaxies and the cosmic web. Yet the mechanism responsible for that transformation remains partly hidden. The field that may have driven inflation has not been identified. The conditions that allowed inflation to begin remain uncertain. The transition into the hot universe is reconstructed through models rather than directly observed. and the primordial gravitational waves that could reveal another side of the inflationary era have not yet been securely detected. This leaves inflation in a quiet but scientifically productive state of incompleteness. It explains much without explaining everything. It allows measurements made across the modern sky to reach toward an epoch vastly earlier than stars' atoms, or even the familiar hot plasma, while still preserving a boundary beyond which present theories become less certain. That boundary is not an absence of knowledge so much as the place where the next questions gather. Inflation may eventually become a confirmed part of a deeper theory, or some more complete framework may change the way its successful predictions are understood. For now, the early universe remains partly visible through the patterns it left behind its largest structures, carrying traces of processes that began on scales almost unimaginably small, and its deepest origin still resting beyond the edge of what present evidence can securely describe.